Test. Okay. Good morning, everyone. Welcome to Friday's first session, which is session 11 on new cryptographic primitives. Our first speaker will be Eshwar Vivek Mangipudi. He's a researcher in Supra Research focusing on cryptography, and he got his PhD from Purdue in 2022. He'll be talking about non-interactive verifiable secret sharing using class groups and applications to distributed key generation. Please take it away.
Thank you, Nusrat. Hello, everyone. I am Ishwar Vivek. Today, I'm going to talk about my work on non-interactive VSS using class groups and its application to DKG. It's a joint work with Aniket Kate, Pratyay Mukherjee, Hamza Salim, and Arvind Tyagarajan. So we all know, like everyone in this hall is pretty convinced by now that threshold cryptography enables decentralization for better security, better privacy, and better availability. And the interest in applying threshold cryptography to blockchain space is evolving and in fact exploding as we speak in the blockchain space across multiple applications. Few of the applications that we can think of are using for threshold signatures, where we use for consensus mechanisms, for transaction authentication, and then applying threshold cryptography for verifiable random functions, where we need randomness generation for Web3 gaming, even for beacon generation for chains, even for wallet management. Over the last 2 days, we have seen several applications, including threshold decryption. So for all these mechanisms, we can think of threshold cryptography as a special case of multi-party computation, where we are trying to compute a keyed function, f of x, keyed with a certain secret key sk. But this secret key is distributed over many parties, and no single party has complete information of this sk. So one of the ways of generating the shares of this secret key among the parties is a protocol called distributed key generation protocol. So distributed key generation protocol, you can think of it as a pre-processing phase of many threshold cryptographic applications. The output of this protocol is secret shares of a certain secret key to each of the parties. And at the end of the protocol, everyone has a private share of the secret key, and they will also know the publicly of the whole system. So each party gets a share, a partial share, which is shared as a threshold secret shared share. And when I say threshold share, the access structure, we call it as T, N, by which what we mean is that any T+1 or more parties can come together, reconstruct the secret key, and up to T corruptions are allowed in the system. And we typically consider at least honest majority in the system to ensure liveness in the system. So with that in mind, the main aim of this work is to design a versatile and efficient DKG mechanism, and hopefully a simple one too. So let's look at secret sharing and verifiable secret sharing, which is a basic building block of DKG mechanisms. The setup is pretty simple. We have a dealer D and total number of receivers, N receivers, including the dealer. And then we define a threshold, which is at least, which is less than N by 2, where N is the total number of parties in the system. And the dealing algorithm takes the secret input of the dealer S as input and generates shares, N shares, which are secret shared as T, N threshold secret shares. And each of the party will be given their own respective share. And any number of more than T+1 parties can come together and reconstruct the secret share. So one aspect of simple secret sharing is that everyone will get a share, but they will not be able to know whether their share is correct or not. So for that, we use verifiable secret sharing, which allows each party to verify whether their share is correct or not. So again, the setting is pretty similar. However, we now have a broadcast channel, and the dealing algorithm, along with outputting the individual shares of the parties, now outputs a public proof, or in some sense, which comes as commitment to the shares or the polynomial. So every party can verify independently whether their share is correct or not, and take respective actions. So in the reconstruction phase, at least T+1 or more parties can come together, reconstruct the secret key, and then verify again as a commitment to the polynomial or the secret. And that's how they will know that whether the dealing was correct or not. So VSS comes in many flavors, and one of the interesting properties one of certain VSS protocols offer is what is called public verifiability. A publicly verifiable protocol offers few of these properties. One is privacy. Of course, if at most T parties are corrupt, the secrecy of the secret key is maintained in the system. But then we also have public verifiability property, which says that anyone can verify the correctness of the dealing as long as a maximum of T parties are corrupt in the system. This is the traditional definition of public verifiability. But in this work, we introduce what is called strong public verifiability, where we say that verifiability holds even when all the parties are corrupt in the system. So we formalize this property and prove the correctness of the protocol against this property. So now we say that the verifiability is guaranteed even when all the parties are corrupt in the system. But if all the parties are corrupt in the system, there is no secrecy. There is no privacy of the secret key. However, the correctness of the protocol is, can be verified and is guaranteed in the system. So let's see why is this important, or where that is, where you can see this property showing up. Consider a simple example of secret sharing, where there is an honest dealer who has generated shares and does the secret sharing. And now if there is a dishonest majority in the system where the number of corrupt parties is more than T, so they can reconstruct to a null value, or let's say they output a bottom. So even though the dealer is honest, he cannot prove himself to the world or to the system that his dealing was done correctly. So for example, if you see voting protocols, a honest voter may have voted and his vote may not even be counted if the number of dishonest parties in the system is more than the threshold T. So, but if the protocol satisfies strong public verifiability, the correctness of the protocol can still be guaranteed even when there's a dishonest majority in the system. So we're going to see, now let's see what is the state of the art of the VSS protocols and which protocols can or cannot support this strong public verifiability property. So let us first look at the interactive VSS protocols. There has been a long line of interactive VSS protocols over the years, where the setup is pretty similar. You have a dealer D and N receivers, and this dealer and the receivers participate in an interactive protocol, where at the end of the protocol, if the dealing was correct, all the receivers accept the dealing. And one of the most recent works appeared by Das et al. In last year in 2023, where they formalized the public verifiability property. So the idea is, to give a basic idea of the protocol, what happens is the dealer forwards each of the shares to the parties along with the commitment to the polynomial. And if each party verifies the correctness of the share, they'll send a signed acknowledgement. And all the signed acknowledgements are collected and quorum certificate is formed, which will work as a publicly verifiable transcript for the protocol. However, you can see that this protocol cannot achieve strong public verifiability. Why? Even if there is a dishonest majority in the system and the receiver just simply does not supply the acknowledgement, you cannot support strong public verifiability in the system. Now let us look at non-interactive VSS protocols and what is the state of the art in them. So the non-interactive VSS protocol is pretty straightforward in the sense like there is a dealer who generates the shares of all the parties, encrypts each of the shares to the respective party's public key, and then generates a non-interactive zero-knowledge proof of correctness of the sharing. And then takes the whole set and broadcasts this set among all the parties. So each party individually decrypts their own share and also verifies the zero-knowledge proof, which ensures that the whole dealing is correct. So they can verify not only that their own share is correct, but the shares of everyone is also correct. So now here we can see that anyone can perform this verification. And so this protocol, this mechanism can help us provide the strong verifiability property. So there are a couple of works which offer the strong verifiable property recently. One is the lattice-based approach PVSS by Gentry et al. In 22, and then Groth's non-interactive DKG in 21. Both of them employ what are called range proofs as a part of this proof of correct sharing, and we'll delve into one of them in detail now. So by now you should be convinced that, I hope you are convinced that Strong public verifiability is an important property to offer, and non-interactive ESS can offer such a property. And one of the non-interactive DKG protocols is by Groth, which appeared in 2021, which uses exponentiated algorithm encryption for encrypting the shares. So the encryption looks like this. You have to encrypt a message M, so you first exponentiate it to, let's say, z power m, and then you do an algorithm encryption on it. So the expectation, they want to do this because they want to have the homomorphic property on the messages so that the proof of verification can be simplified. However, there is a challenge. You cannot encrypt large messages in the exponent because we assume D-log, discrete log is hard in this group. And so you cannot decrypt large values of M here. Let's say if M is 256-bit, you cannot decrypt the value directly. So what do they go for? So they go for what is called chunking. So they divide the 256-bit value into, let's say, 16 parts of 16 bits each. Now they generate 16 ciphertexts for each of the chunks. And now when the receiver decrypts a smaller chunk, he can just brute force or use an algorithm to decrypt the 16-bit value. Now he'll decrypt 16-bit values and finally concatenate all of them together. But using the process of chunking entails them to actually go have another proof showing that each of the chunk is of a certain smaller range. So which they call proof of chunking, correct chunking. So which involves range proofs and in their case an approximate range proof. So being unable to decrypt the direct to larger message in the exponent actually increases the number of ciphertexts that you have and also increases the size of the, adds an extra proof that they need to add to the total broadcast length. So that increases the total broadcast length. But what if there is a mechanism which ensures that I can directly decrypt the message directly from the exponent even though if the message is large? So enter class groups. So for the purpose of this talk, we can think of class groups as large groups with unknown order where discrete log and even DDH is hard. But they have subgroups where discrete log is tractable and solving discrete log is easy. So now let us look at an exponentiated algorithm encryption in the class group setting. So here G is a generator of the larger group and F is a generator of the smaller subgroup where discrete log is tractable. So now to encrypt the message M, the way we encrypt is we exponentiate we generate F to the power of M, and then the encryption looks like what's being shown. So here now I can directly encrypt a 256-bit message and decrypt the same at the receiver. So suddenly you do not have any chunking, you do not need any range proofs or proof of correct chunking, making the system very efficient, and it simplifies the design a lot. A point to note is that there is a recent independent work by Caswado and David which also uses class groups, which we are going to compare against in the coming slides. So let us look at the whole protocol. So before the start of any VSS protocol, so especially in the non-interactive sense, you are encrypting the share to each of the receivers. So each of the receivers should first register their public key. So the way you typically do is they publish their public key and also produce a zero-knowledge proof of knowledge of the secret key. So here we cannot directly use the existing Schnorr mechanisms because now we are operating in the class group. So we produce a proof of knowledge of the secret key in the class group setting, which is roughly based on the Schnorr proof of knowledge. So once that registration phase is done, then you have the dealing phase where the dealer generates the random polynomial, generates the shares of each of the parties, and does a class group exponential algorithm encryption of each of the shares, and then also generates a proof of correct sharing and broadcasts the whole transcript. So each of the receiver decrypts their share by first directly decrypting this F power their share. And then because D-log is tractable in a class group, they can directly decrypt their own share. So the proof of correct sharing is also pretty straightforward. I'm not going to delve into the proof, but it's a simple 3-step proof where a couple of steps are Schnorr-based, one in elliptic curve group and other in class group. Then when we have one simple check where we ensure that the commitment to the polynomial corresponds to the encryptions of the shares. So with a non-interactive VSS in mind, how do we get a non-interactive DKG? So I'll just show a generic construction how to go about it. It's a pretty straightforward mechanism. So I'll show it to illustrate it with a simple example with 3 parties, when the threshold T is equal to 1, where at least 2 parties are needed to reconstruct the secret. So we have party A who samples a value small a, and then just does a non-interactive VSS generating 3 shares for 3 parties. Then you have party B comes into the picture, does a non-interactive VSS of random sampled value B. Similarly, C comes into the picture and does a non-interactive VSS of value C. And then they forward the corresponding shares to each other. So here, party A gets shares B1 and C1, party B gets shares A2 and C2, and party C gets A3 and C3. So now, locally, they just add their shares and obtain partial shares. It so happens that these shares actually will directly correspond to the secret shares of the system secret key, which was a summation of A, B, and C. So you can see that all the computation has been done locally. There is no interaction between the parties. So a non-interactive DKG can be built directly from a non-interactive VSS by simple local computation. And we already mentioned that our non-interactive VSS protocol offers strong public verifiability property, and this property is carried directly into the DKG protocol. So a strong publicly verifiable VSS implies a strong publicly verifiable DKG. So what does this guarantee? So what it guarantees is, even when there is no privacy for the secret key SK, the correct distribution of the secret key and the public key can be guaranteed. So when this is applied to scenarios like a distributed VRF, what it ensures is that even though unpredictability of the final VRF output cannot be guaranteed, the correctness or unbiasability of the VRF value can be guaranteed. And because of this strong public verifiability property, so the support for asynchronous networks comes in some sense for free. And we can also use imperfect broadcast channel for broadcasting the shares. What it ensures is that we can use blockchain now as a broadcast channel. So suddenly all the applications which use blockchains can use this non-interactive DKG mechanism, because now the blockchain can be used as a broadcast channel. So we implemented this protocol in Rust using the Bicycle library and Miracle library for the cryptographic operations. I'll talk about a few details there. And then we use the BLS 12381 curve for the commitments of for the polynomial commitments, etc. And then we actually realized the Groth21 protocol. When the Groth21 protocol actually comes with what is called forward secrecy with a binary tree encryption. So we had to remove the binary tree encryption so that the comparison is fair. Of course, once you remove the binary tree encryption, it makes the protocol faster, and now we can compare it fairly. So the Cashwater David work, we also implement their work for Rust for comparison, and then we use the hot stuff SMR for the broadcast channel. Finally, we deploy them on GCP instances with 16 cores and 16 GB of RAM. And we set the parameters to ensure a 128-bit security, and all the shares of all the parties are 256-bit shares. And with that, once we employ the BLS 12381 curve, all the commitments will be 384-bit values. And then we generate the class group parameters to ensure this 128-bit security. And in a compressed form, a class group element will take 1752 bits. Now let's look at the performance, how the non-interactive DKG that we propose performs against the other protocols. So we are showing the total broadcast length, total length of the transcript that we broadcast across the system. Here, as I already mentioned, because of directly we are encrypting instead of chunking the values, so we save a lot. However, with the increase in the size of the element, so we lose a little bit. So you can see that then, at let's say about 150 parties, we are performing at least 5 times better than the Groth DKG. So this is the broadcast length we are talking about. And the CDVSS also performs pretty similar to our CGVSS, which is the class group VSS. Now looking at the DKG numbers. So here I'm showing two graphs. So when I'm actually performing the DKG, you don't need to wait till all the N parties publish valid secret sharings. Because at only T+1 valid sharings are sufficient, your DKG protocol can go ahead with the first T+1 values. So I'm here showing the timings for the T+1 dealings and also the N dealings. So roughly for 30 parties, CGDKG takes 6 seconds, whereas Castro David CDDKG takes around roughly 12 seconds. Here, the red line, which is a Groth DKG, has been implemented, realized using the Miracle library. However, if you employ BLST library, the red line can come much closer to the blue line. However, one thing to note is that there is no hard and fast rule that you need to use this BLS 12381 curve in our protocol. We can use any elliptic curve. So if you use, let's say, SecP 251, 256K1, the operations are much faster. So we went for the BLS curve for fair comparison with the other protocols. Similarly, for the end dealings, for 30 parties, you have CGDKG taking 8 seconds and CDDKG taking roughly 16 seconds. So finally, to summarize, what we propose is a very simple, efficient, non-interactive DKG protocol to generate discrete lock keys. I think a couple of days ago, Alan presented a DKG where they produce keys in as a group elements. This work, we produce keys as scalar elements. So we have a very simple design, very efficient, and the community is just getting started with the class group implementations. And we hope that with better implementations and better study on these protocols, the speed is only going to get increased down the lane. And along with it, we also identify an important property of non-interactive DKG protocols, which is a strong, publicly verifiable property. We formalize them using UC models, and we also have a rigorous security analysis. So the paper is going to appear in CCS this year, and you can have the ePrint version through the QR code. Thank you. If you have any questions, I'll be happy to take.
Thanks for the great talk. Are there any questions? Yeah.
Thanks for the talk. Really nice work. Really happy to see this class group-based cryptography take off.
Thank you.
So I had a question first. Micro benchmark-wise, how long is a 256-bit exponentiation in a class group with Bicycle? Is it like, are we talking 300 microseconds, 500 microseconds, or something like that?
I would assume roughly 10 times more than a normal exponentiation, but I need to check it. Yeah.
10 times more than a BLS, yeah. And I guess you mentioned you have this proof of correct sharing, yeah? That proves that the encrypted things are the same as the committed things. How long does that take? Do you have a...
So I only have the total numbers, but I can get back to you with the individual numbers on micro benchmarking of each of the steps.
And the DKG numbers you showed, those account for networking consensus?
Yeah, networking delays. So I mean, which is each along with the round trip time. So from the starting of the dealing to and each of the parties verifying. So just for computing the time, what we did is each of the parties sends an acknowledgement. So when the dealer receives all the acknowledgements, we consider the DKG to be done. So ideally, in non-interactive world, there is no acknowledgement, right? But you cannot find the timing like without an acknowledgement. So that's how we complete the round trip time, and these are the numbers for that.
And so are you using a consensus protocol, or is it sort of manually benchmarked in an artificial setting?
No, so we run all the VSS protocols parallelly, and then each of the parties, once it finishes the VSS or finishes the DKG, it sends an ACK, and the dealers will compute the total timing between first dealing to the first completion of all the acknowledgements.
Thank you.
Yeah, thanks. But I'll get back to you with all the benchmarks. Thank you.
Super cool work and great talk. Thanks a lot. I'm also a great fan of class group-based crypto. You mentioned this work which uses lattices. Can you give us sense how it would compare with these works?
Yeah.
Like in these graphs, in these figures, on these slides, you don't have these lattice-based schemes. I
Yeah.
just wonder
so
how
lattice-based schemes, so they're asymptotically efficient. So let's say you'll start seeing the benefit, let's say after 1,000 users, but in the 200 or 100 node regime, they're extremely inefficient. Let's say if a single VSS here takes, So here, so this is 30 nodes, right? So 30 nodes doing 30 VSS protocol, VSS instances. So if you see, if it takes 20 seconds, there it will be going to take, I think rough mention is 50 seconds or 100 seconds of that order. So not even comparable in sub 1,000 node scenario. So, but over, let's say if you have 10,000 nodes, they're asymptotically very efficient. So then you will clearly see the difference between lattice-based and these schemes. So because this is a continuously increasing graph, but their protocol probably will stabilize at some point.
I gotcha. Thank you.
Yeah, thank you.
We have time for one more question.
Yeah.
Hi, thanks for the talk. You mentioned at some point that with this protocol, finally we can use blockchain as a broadcast primitive.
Yes.
Can you elaborate on this? Why can we not do this with other, like Gennaro et al.-based DKG protocols?
So yeah, so when you say broadcast channel, when you say reliable broadcast channel, right? So it also like implicitly assume that all the parties will receive the output, and all the parties are whatever is. So blockchain is not a ideal broadcast channel in the sense you can think of it as a delayed broadcast channel, because the moment you publish, there is a delay before which it reaches all the parties, and all the parties may not be live to see, and you can also come back later to see the values, right? So blockchain is a slightly different model than an ideal broadcast channel that we assume for all the parties, for all the other protocols. So it's an interesting model. People are trying to model it as a delayed broadcast channel these days.
So in short, it's about combining the models or about handling the delay that there is on the blockchain or something like that.
Yeah, so it's not an ideal broadcast
Yeah.
channel like what we assume in the community till now.
Thank you.
Thanks.
Let's thank the speaker again.
Thanks a lot.
Okay, our second and the last speaker of this session is Orpheas Stefanos Tifronitis Litos. He's a researcher at the Imperial College London and Common Prefix, and he'll be talking about Bitcoin Click channel-free off-chain payments using two-shot adapter signatures. Please take it away.
Good morning, everyone. Thanks for showing up for this morning session. So we're going to talk about Bitcoin Click, which is work that has been presented at ACNS this year. So what I'm going to present to you today is a construction for a commit chain on Bitcoin, or rather with a little asterisk there. We're going to talk about that later. First of all, what is a commit chain? Let's imagine a bunch of apparently quite active users who send payments to each other, and they wouldn't like to pay all the high fees on Bitcoin, so they would like to package their transactions, their payments as a single on-chain transaction on Bitcoin. And that could happen periodically, like every now and then, package the new payments that took place into a single transaction. This is essentially what a commit chain is. It's kind of a side chain, but it commits to the main chain, Bitcoin in this case. So first, let's get some motivation for that. Blockchains are quite expensive to use, so it's a good idea to find such solutions as a commit chain. These family of solutions are layer 2 solutions, and this is much cheaper because you kind of touch the blockchain less, right? And why do we work on Bitcoin? So there's a number of reasons to make that choice. First of all, it has a lot of robust security analysis behind it, so we build on solid foundation. And then its scripting is not Turing complete, which makes our task harder, but it also shows that it's kind of a common denominator of mostly all other blockchains. So if you have any kind of scripting capabilities, then you can do that on your own blockchain. And of course, Bitcoin is has quite some value locked under it, so it makes sense to just make Bitcoin more liquid in one way or another. And one could say, but we already have layer 2 for Bitcoin at home. Why not stick with channels? And the reason is that channels are hard to manage. Channels have all this baggage of having your money locked in a specific channel, if you're familiar with this literature, and there's a bunch of issues there. There's an overlay network that might break, and it might break in ways that usual networks don't, like channel imbalance. And a solution to that has been proposed, and it's hubs, payment hubs, which have channels with everyone. This is, of course, a centralization hazard, and in practice, it needs the hubs to lock up immense amounts of collateral to enable any payment possible. And this means that they have a lot of opportunity cost that the users then have to pay in forms of fee. Our protocol will still have collateral, but much less than O of N, essentially less than hubs over payment channels. So let's see exactly what we're after. We want anyone in the clique to pay anyone else. So the name clique comes from the graph where everyone is directly connected with everyone else. Parties should be able to leave at any time without being beholden to others with their own money. There should be a maximum finality time, maximum liveness parameter, essentially. And we shouldn't add any extra trust assumptions apart from the ones on layer 1, i.e. honest majority of power. And we want to minimize as much as possible the on-chain transactions, which is the goal of any layer 2, essentially. So let's introduce a little bit how things work on Bitcoin. This is a Bitcoin transaction. It has a single input and a single output. Over the output, you can see how many coins, how much value is locked in this particular output. Under the output is the rule by which one can spend this output. In this case, party A, Alice, is the only one that can spend this output. And how can she do that? She can do that, for example, with this other transaction, which has a single input, which carries her signature, sigma, and it has 2 outputs. The first output has C coins, C of those 3 C coins, and the remaining 2 C coins can be found on the other output. The first output has a slightly complex spending rule. We're going to introduce the notation here. This can be read as this output can be spent either by A or by B. But B is encumbered with a time lock. So B has to wait for time T before they can spend this output, whereas A can spend it right away. The second output, on the other hand, can be spent if C and D agree. So this is the notation that I would like to introduce. And let's see a strawman solution, a naive solution to the problem of Bitcoin clique. So let's assume an operator. We will have an operator later for this construction. That at this stage is trusted. And so parties P1 through Pn have each C coins, and they all create a transaction collaboratively that join all these coins together into a single output controlled by the operator. So the operator can now keep track of what payments are happening off-chain among the parties of the clique, and keep track of who owns what. Later, if a party wants to join the clique, they can just ask the operator to have a transaction like this and add their C coins to the pot. You will notice that transactions that are managed and controlled by the parties are green, and transactions managed by the operator are black. Later, if a party wants to get out of the clique, they can just ask the operator to give them some money, the money that it belongs to them. Of course, this construction trusts the operator, and the operator could very well run away with the money. And you have to trust the operator that they will not run away, that they will give you back your fair share of the money. So this is not a trustless solution. Let's go towards a actually trustless solution. So the main idea behind our construction, which safeguards the security of the users, is this idea where we have, at any point in time, we have 2 copies, 2 outputs waiting to be spent. And each output, as you can see, has the entire sum of the money in the clique. Where does this money come from? Because half of it, the NC part on S1, on the step transaction 1, comes from the parties. The other half, the NC coins on S2, comes from the operator. So this is the collateral that I was talking about. And this is, you could say, one of the drawbacks of the system, that the operator has to put up as much collateral as the entire value of the clique. But this is still way less than what the operator of a hub in a payment channel would have to put up. So it's still an improvement compared to previous work. And you will notice that the spending condition for both of these outputs are either the operator after a time lock or some rule C that we will look at later. And this rule C is what is not encumbered with a time lock, and this means that it can be used right away. And in fact, this will be accessible by any user in order to take back their money unilaterally. And if you notice, the time locks of the two outputs differ by T. And that's on purpose, because that means that if both of those outputs are on chain, then the first output will expire, the time block of the first output will expire first. And it then should be spent by the operator as quickly as possible with a new step transaction that reflects in some way the new allocation of coins. What has happened essentially between the time that S1 was published and S3 was published. And so if the operator does not spend S1 right away, or if it spends it in a wrong way, then the parties will use S2 to get their coins. And S2, notice that it's still locked with the time lock, because the time lock of S1 just expired. So the time lock of S2 has T time more until it expires, and so the operator cannot do anything with the output of S2. This idea is the central idea that safeguards parties' money. Later, when S2 expires, you see the next output that expires is S2, because the time lock of S3 is 3T. When S2 expires, when its time lock expires, the operator moves on to spend that output. So it alternates spending between one and the other. And this is the normal state of affairs. This is the normal evolution of a channel in which there's a single transaction every time T, which is a configurable parameter. And this transaction is quite small. It has a single input and a single output without complicated logic. So this keeps the running costs low. And of course, these transactions can reflect any number of payments in the click. So moving on, what is this secret C sauce that we used there? We have to open this up and see what's going on there. So this is where we introduce check template verify, which is an opcode that is not available on Bitcoin today, but it might get added in the future in the form of actually this proposal with this name, or if we go with OPCAT, which is a prime contender to enter Bitcoin script, we could emulate it with that. And so how this script is read is that it can be spent by the operator after time 4T, or by transaction T1 at any point in time. Transaction T1 is specified precisely, almost precisely, in the output. All the relevant parts of T1 are specified already at the time of the creation of S4. So that means that any party can come around and use T1 to spend this output, but they can't use anything else. This is kind of the magic sauce that check template verified gives us, which is not possible otherwise. Being able to specify early what transaction can spend an output. And so we will briefly go for some cryptography here, which will be used a little bit later. I'd like to introduce the concept of adapter signatures. And this is something that has been formalized in the literature, but I will just give you the very basic idea of the main protocol that motivates this primitive, which we will use later. We have Alice and Bob. Alice has a public statement Y capital and a secret witness Y small. And she wants to sell this witness to Bob, and Bob wants to buy it. The public information for now are the public keys, the public statement, as well as the transaction by which Bob pays Alice. This transaction is not signed, it's not on the blockchain, and Bob wants to only sign it if he's reassured that he can receive the witness from Alice. So the steps of using an adapter signature to achieve that is that first Bob, as we say, pre-signs. That's the first algorithm of the primitive. Pre-signs the signature, the transaction, using its own secret key and the public statement. This pre-signature is not yet a valid signature. However, Alice can use the adapt function of the adapter signature scheme, using her own, apply the adapt function on top of the pre-signature, using her secret witness to generate a full signature. This full signature is a valid signature by Bob's public key. And so now the transaction is fully signed, and Alice can publish it on the blockchain. And Bob can receive the signature either directly from Alice or by looking it up on the blockchain. What this achieves is that in one fell swoop, Alice is paid as the transaction is valid, and Bob can use the last interesting function here, extract, to get the witness, the secret witness, using the pre-signature, the signature that has been adapted by Alice, and the statement. And so Bob learns why, if and only if Alice is paid. So we achieved an atomic swap of a secret for money. In our case, in our setting, we use an extension of adapter signatures, which is a very simple modification. Instead of Alice having just one pair, she comes up with two pairs. And the secret that Bob wants to learn is the sum of the two secrets, the sum of the two witnesses. If Bob learns only one of the two witnesses, but not both, then Alice's secret is safe, because the other half cannot be computed by Bob. Let's see how we will exploit this to offer security to the operator now. And by the way, I will show you how the unilateral exit of a party works. These are the two outputs that we discussed before. This I use now S1 and S2. That could be any n, any two subsequent numbers, any two consecutive numbers. And so let's say that player one now wants to exit the click. In this click, we assume that there are just two parties for simplicity, with C coins each. What T does is that he publishes, what player one does is that he publishes transaction T1, which is specified on the CTV there. So he can only use that transaction. And what this transaction has is two outputs, one per party. And player's two output is just like player one's output, they just don't repeat the script. And what the script says for player one is that this output can be spent either by the operator after a time block, or before the time block expires, or at any time. Player one can spend it, but he also has to disclose a witness to this statement y1, 1. And that's what he does when he publishes the so-called out transaction, O1, 1. This transaction allows P1 to spend its own money, but after a time lock T prime. The party that now can spend the money before the time lock is the operator. But the operator needs two pieces, two witnesses, not just one. With this transaction, the party P1 published a signature that is this signature that corresponds to the witness Y11. And this is exactly the adapted signature that we discussed before, one of the two. This signature thus can be used by the operator to extract the secret Y1, the witness, that corresponds to Y1, 1. At this point, if P1 just waits for time T prime, the time lock will expire, and he will be able to take its own money and go do whatever it wants with it. And the operator cannot exercise its spending method on the out transaction, because the operator knows only the secret Y1, not Y2. However, look what happens if P1 becomes greedy and tries to take its money from the other output as well, which now it's not entitled to, because P1 only is entitled to C coins, not 2 C coins. So nevertheless, P1 can still publish transaction T2, which has a similar script as the first one. It's just that this is locked with Y12, the second statement. And if the party one goes on to use transaction O12, similarly to the first path, they will have to use this signature sigma 2, from which the operator will then learn Y2. And by learning Y2, now the operator is able to spend and use this Spanish transaction and spend P1's money however they seem fit. So this way, the operator is safeguarded from attacks from malicious parties that try to use both available outputs to take their money. Parties should only use one of the two outputs, not both. So in this way, we have managed to close the circle and offer security to both the users using this staggered approach of 2 outputs, and to the operator by using this two-shot adapter signature trick. There's a number of limitations to this work that we would like to explore further in the future. We do need an operator, which luckily is made and trusted. And this operator has to put up quite some collateral. Also, if you have noticed, this whole structure has a single denomination. This can be avoided in a naive way by just setting up many clicks with different denominations and use the same approach as in cash, which is that you have a number of denominations and then you mix and match with them and you can make any payment. Or we can come up with even more efficient versions where we don't need different clicks for each denomination, but we somehow combine them into less. And this current construction offers no privacy because all payments are disclosed between, among parties are disclosed publicly within the click at least. This is needed for parties to check that the transactions in the CTVs are correct. But we achieved a number of goals, which is, as we wanted from the beginning, to make it possible for anyone to pay anyone else in the click. Parties are free to leave unilaterally using the technique we saw. There is a maximum time to finality, which we can calculate. The operator is assumed to be Byzantine, so no trust there. The number of transactions are minimized as much as possible by making sure that during normal operation, there is the number of transactions is completely constant in the number of users and in the number of payments. And what I haven't put up here is that in case of a closure of a channel, a unilateral closure without collaboration, the cost is logarithmic in the number of parties in the click. So yes, because you have to publish a logarithmic number of transactions on chain to leave the click. In the example we saw, there were just 2 parties, so this logarithm didn't show up. But it can be argued that this is only in the pessimistic case, so it's not too much of a burden. The operator is also secure. This is a new requirement that wasn't there initially since we didn't have an operator, hopefully. But since we have the operator, we have to offer them security, and we do. And what I haven't presented either is that we have set up a system of graceful recovery after closing starts. So if the click starts to close by any one member of the click, that doesn't mean that it has to close to completion and every party has to go home with their money. No, the parties that want to carry on with the click can relatively cheaply recover the click and carry on with their protocol. Thank you very much for your time. This has been the end of the talk, and there's a few extra slides for questions, and if there's time, I can show you, for example, how payments are carried out.
Thanks for the great talk. Are there any questions? There's one question.
Good morning. Great presentation. Very much enjoyed that. What are some of the applications that you think in this type of construction? Are you thinking just in terms of fast and cheap payments, or did you have any kind of like maybe Turing-complete applications in mind in this construction?
So this construction is only for payments. So essentially, the way it's constructed, it gives you less power on the L2 than Bitcoin does, which is sad. But it could be extended to more scripting capabilities, possibly. That's an interesting further direction.
You gave an example with 2 users. Can you tell us a little bit about the challenges of making it to multiple users, if that's also a high number?
So here is how it looks like to have more than 2 users. The difference is that essentially there's a binary tree that is created in our construction. In this example, we have 4 users. And the transaction T1 splits the money in 2. And then you have to do a second level transaction, a T2 or T3, in order to reach your level. And this scales logarithmically. There has to be some research on the branching factor. We can change the branching factor. This was just as a proof of concept construction. You can go for a higher, I think the ideal would be to go for a different branching factor for early stages and then a different branching factor later, closer to the end, so as to minimize the expected number of transactions. If you were to go for a flat structure where like T1 had all the outputs already, that would lead to other problems. And you wouldn't want to close the click too quickly. That's one major issue there, that if only one party wants to close and the rest want to continue, then only one branch is evoked and the rest of the branches can be closed faster. So less outputs are put on chain eventually.
So you mentioned that users can leave unilaterally at any time. What about the operator?
The operator as well. So if we take a look at this situation, there is, at any time where T expires, the operator can do whatever they like with the output of S1, including going home and breaking the click in one fell swoop. The other parties are still safe by the other output, of course. And so the operator takes back their entire sum of money. One thing that I haven't brought up is fees. Fees will be paid by the users to the operator, and the operator will then, probably out of band, and the operator will then use its own, alternate between spending fees from each output. So that gradually reduces the money in the click, but at a very slow rate because the transactions are small.
Yeah, I personally would like to see covenants happen on Bitcoin, but since I hope this will be even more the reason for them to adopt it, but in the absence of them, would you be able to maybe relax your assumptions a little bit and use perhaps like a committee to emulate a covenant?
Yeah, absolutely. This could be possible to have essentially you would go back to the construction, this naive construction, the Strawman solution, but replacing the operator with a committee. And so, I mean, it's not palatable to trust a single person. It is a little bit more palatable to trust a subset of a committee, maybe. I find these constructions not so interesting anyway, and there is a social reputation structure going on there, so I think that it makes analysis more complicated, and at the end of the day, it opens the doors to attacks that we wouldn't like to see. Trustless solutions are the way to go, in my opinion. Unfortunately, we can't make that work with today's Bitcoin, and that's why we're sorely missing an update.
Yeah. Thanks for the great talk. Let's thank the speaker again. This concludes the first session of Friday, and yes, break should be ready. Hello, everyone. Welcome to Friday's second session, which is session 12 on DAOs and more. And our first speaker is Michael Zargam. He's the founder and chief engineer at Block Science and research director at Metagol. And he'll be talking about open problems in DAOs. Take it away.
Great, thank you for having me. This is going to be an interesting talk because it is going to be way less technical than the ones we've seen so far, which is a bit of a role reversal for me. I usually get stuck giving technical talks to non-technical audiences, so giving a non-technical talk to a technical audience is going to be, well, we'll see how it works out. So today's talk is Open Problems in DAOs with an emphasis on why you should care, and this project has been facilitated by Metagov. It involves an extremely large number of collaborators. I was asked to come and give this talk today because Josh Tan, who was the first author of our paper, had to go to DWeb Camp and attend to some other, hopefully related, decentralized systems business. But I wanted to emphasize the breadth of the background of the authors on this paper because we have computer scientists, mathematicians, lawyers, ethnographers, people who work in political science, as well as on economic systems. And really, it's been a really pleasure to collaborate with this many great folks with this many great backgrounds. The paper itself, this is a rough overview of the outline. You can find it on arXiv. We made an effort to sort of sketch out the territory across computer science, economics, ethics, law, organizational science, political science, and philosophy. And to be totally honest with you, that wasn't everything that we bumped into, and worse yet, it feels a lot like this. So thinking about DAOs, it's interesting, right? You have to deal with the question of what is an organization before you can worry about the questions of autonomy and decentralization. And in the particular case of DAOs, we're exploring the ways in which new technologies create new capabilities and the way those new capabilities are leveraged by groups of people towards their collective ends. And so in an effort to build out a map to go survey the field, we wrote this paper and invite everyone to fill in the gaps, identify bigger gaps, and where possible, contribute to expanding that field. Now, I can't really do justice to everything that's in this paper in a short talk, but I am going to start by trying to motivate for you why you should care about DAOs, when I think most of the focus of this conference has been on technical capabilities and meaningful improvements to those technical capabilities. The fact is that DAOs, or in various ways technically constituted organizations, are being used to attack some pretty major issues, and that includes with your colleagues at your foundations, at your companies. And some of the main focus areas that we highlighted in the paper are sustaining open source software, which in a sense is the ability to create and maintain the technical infrastructure itself, but also other technical infrastructures that require funding to produce forms of value that are not strictly monetary. We've seen a growth in interest in democratic governance of artificial intelligence, or just more generally the democratic governance of computational spaces. When we start gathering data, when we start leveraging it to create both public and private benefits, a bunch of questions arise about who owns what, under what circumstances they have the authority to make decisions about who can use those tools or derive monetary benefits from them. And finally, regenerative finance. There's been a growing number of organizations focused on how these new technologies can change essentially the political economy that drives sustainability projects. I think it's a recurring theme that our market mechanisms don't actually discover the kinds of value that we want in the world, and we've identified that organizations are taking blockchain and blockchain technologies, decentralized networks, and smart contracts into this venue, despite headwinds where in many sectors it's viewed as the exact opposite of that as a result of the origins of proof of work. I'm going to take a step back and talk briefly about me so I can share my particular part of this research or my work on DAOs. And that's going to take one step away from the broader everyone in this author group's expertise. I'm an electrical and systems engineer. I got my PhD from the University of Pennsylvania in 2014. My day job is as the founder and chief engineer of a small private R&D firm called Block Science. Blocks as in modular components, although we do quite a bit of work in the Web3 space, so no complaints about the reference there. I'm also a board member and a research director at MetaGov, which is a laboratory for digital governance, and this complements the technical role where I'm working with community members and projects to understand and explore the ways in which these technologies affect governance. I'm going to recommend that anybody who's interested in technical systems impacts on society more broadly and interdisciplinary work have a look at this map. It's from Berkeley. It's the Cyber Physical Systems Concept Map. It's clickable. All the things are defined. I think the first time I referenced this as applicable to blockchains was in a 2019 paper with Sherman Voshemger, but I come back to it over and over and over again, which is a cyber-physical system is a collection of mechanisms that is controlled and or monitored by computer-based algorithms tightly integrated with the internet and its users. Given that and that definition and this concept map, I find it hard to look at blockchain-based systems through any other lens. I realize that it's important to take an interdisciplinary view, but the reason I like this particular domain is because it's already entangled in our existing infrastructures, and it brings into it questions of economics and governance through the provision and maintenance of infrastructures where there are humans in the loop, the systems are distributed, intelligent, real-time, and so on. And so that's really not a main focus of our paper, but it's something that I wanted to provide as grounding for my interest and my thoughts on DAOs specifically. So from the paper, we draw on the most canonical definition of DAOs, at least in the Web3 space, which is Hassan and DeFelipe. DAOs are organizations governed by a smart contract, typically deployed on a blockchain that autonomously enforces rules for interaction amongst the members. However, in our paper, we acknowledge that DAOs also belong to a larger class of digitally constituted organizations. Organizations governed through computational artifacts such as software, hardware, and protocols. And so in this view, we're interested in more than just organizations that are grounded in a set of rules that are executed and validated on chain, but we're interested in the organizations themselves. I'd like to share this meme from my friend Eric Alston. He gave a talk at the Ostrom workshop on litigating the ledger, civil liability for DAO controllers, and he introduced his talk with this meme, where we see that there are a lot of things that just don't make the smell test. Like some people might say, hey, this is governed by a smart contract, but what are the rules actually, and do they make any sense? Do they do they actually serve the purpose that was the stated purpose of the group? Is it actually just underwriting a scam or a rug pull? I don't know. Is it a DAO if it's governed by a smart contract, but the thing it's doing is not coordinating the activity of a decentralized group, autonomous from an external authority? I'm not really sure. So drawing on a piece of work that I did with Eric and several other co-authors, we laid out the definition of a constitution, at least insofar as it's relevant to digitally constituting organizations. So the function of a constitution is to delineate the boundaries of a particular organization or entity, entrenching elements of its composition relative to that organization's regular process of decision-making. So this is like secondary rules, rules about how rules are made. This can include things like changing parameters or upgrading contracts if you happen to use upgradable contracts. But it also is part of what holds that boundary against external context, legal, social, economic, and environmental forces. For the most part, we look at DAOs in terms of their robustness, their ability to be unperturbed by external forces. But we've seen in practice that they are, in fact, affected by those forces, because as long as you can influence the decisions of actors or operators within the organization, you can affect the organization. So this constitution operates to reinforce the coherence of that entity. It gives it persistent identity in the face of both internal and external pressures, and evolve through its interactions with both its members and its environments again, while retaining its identity. And I think the key here for me is that in order for something to be a thing, it has to have some notion of persistent identity over time, and that persistent identity over time is generally given to it through something constituted, something that changes more slowly than the other elements. So it can have behaviors, processes, decisions, events, proposals, outcomes, debates, arguments, etc., but its identity, it persists. And I think that also invites us to think about the circumstances when identity breaks down, like when a DAO goes through a fork. And what would that even mean? Well, you generally have to fork the code, but you also have deviations in the set of commitments and participation and involvement of the participants. So more memes. Another reason why you should care, especially since this is a pretty technical audience, is as Gabe Shapiro put it in the MetalX white paper, the age of lawyers is over, the time of the coders has come. Now, I'd probably soften that a little bit, but I like the direction we're going here. Thinking about this from an infrastructure standpoint, we have these organizations, these decentralized networks, DAOs, protocol guilds, Borgs, et cetera. Whatever the organizations, the activities that we are organizing and the groups of people participating in those activities, they are using, operating, monitor, maintaining, and governing infrastructures. And those infrastructures are in turn enabling, facilitating, standardizing, automating, decentralizing the activities that they undertake. And this is actually a natural feedback loop. We don't really have institutions without any infrastructures, because if they had no infrastructures, they wouldn't be constituted in the sense that they had persistent identity. They have patterns of behavior that are entrenched in tools, in rules, in processes, et cetera. And getting standardization and scaling generally comes with building infrastructure. And conversely, we don't really have any infrastructures without institutions, because there needs to be somebody to actually maintain that infrastructure. Sure, if it works once, but if you need it to happen time and time again to produce that persistent identity, then you're going to have some pattern of behavior that actually uses, operates, monitors, maintains, and governs that infrastructure. So I prefer this version of the meme. So not so much code as law as algorithms as policy, and first wrote about this with another one of the co-authors from our survey paper, Kelsey Nabin, in 2020. Drawing on other collaborative work with Kelsey, we pushed on this notion of a constitutional archetype where we strike a balance between mutability and immutability, and that the key here is to make sure that the set of things that one can do to modify the organization or the organization's core rules, its constitution, is small. You don't want it to be none, because then you have no adaptive capacity, and that there are certain kinds of emergent threats you won't be able to deal with. But on the other hand, you don't want to be particularly mutable, because you need that constancy, that trust, that identity. And in this case, the trust is, you could say, a kind of confidence that the rules won't be violated, or a procedural legitimacy. You still need to have enough room within the organization's decision-making capacity to pursue some sort of shared purpose, even if that purpose is just the continued maintenance of the infrastructure that is being used. So one more meme from this group. So we have the humans are in the DAO. This is from Amber Case's The Human Side of DAOs podcast, and for reference, Amber is also a research director at MetaGov and one of the founders of DAO, which is a DAO tooling DAO that operates primarily in the Cosmos ecosystem. But the emphasis here is on the fact that we can't separate the humans from organizations, that they are part of the organization. In fact, they animate it in the sense that they provide the impetus to do something, to pursue a purpose, as it were. And so adapting from another earlier work that's cited in our paper, we have this articulation of an institution, or potentially a DAO, insofar as the technical infrastructure is sufficient to qualify under your preferred definition of DAO. We have humans acting underneath the rules. So we've got tools. Those tools both provide and enforce rules about what actions can be taken and what happens when you take them. And those rules themselves are akin to this constitution. And if you want to make amendments to that underlying rule set, rather than simply apply that rule set, then we would consider this governance. And that governance can be directly over the technical infrastructure, but it can also be influencing the norms that affect which decisions agents take within a particular context. I prefer using MEV as an example of a circumstance where norms have emerged, because particularly in the Ethereum context, where whether or not a sequence of transactions is valid ultimately determines whether or not it can be accepted as a block, doesn't actually change the fact that there are things that people consider kind of inappropriate. And we've seen the emergence of things like flashbots to essentially standardize and set behaviors that are more acceptable. We've seen changes in the way that research is directed towards things like PBS as a result. And prior to actually affecting any direct change on a network, or even instead of affecting a direct change on a network, you can see the emergence of new tools, new practices, and new behaviors within the context of a technically or digitally constituted system. So this sort of brief exploration of DAOs is meant to get you at least interested. It also implicates the topics explored in the Open Problems in DAOs paper. I personally contributed mostly to the computer science and economics sections, given my particular background, but it was really compelling to get to see that work interwoven with the expertise from researchers and faculty in law, organizational science, and political science. This particular paper is meant as an invitation to start a new area of inquiry, again, more with the kind of what I would call the traditional engineering vibe, where we have to build out an interdisciplinary set of skills that operationalize the technology that we're developing in real-world contexts, which means making pragmatic assumptions about the world in which those technologies are being deployed and trying to, in essence, make it easier and more practical for those tools to be used by people who are building organizations. And again, there's a lot of open questions here, and there are a lot more open questions that haven't been asked. And so our preference is for people to reach out to us. This link is a Notion site as opposed to the canonical link, which is on Archive, because this link provides access to how to contribute. And we would really like it if people both helped build out the number of fields and the questions being asked, as well as beginning to fill in and write papers trying to answer some of these questions, because we think that is the natural trajectory of bringing this technology effectively to the world. So thank you very much. So my goal was to do questions as a way of getting to all the content. So if people want to jump into any of the specific topics, I can also answer questions there. But there was no way to cover everything, so this seemed like the right approach.
Yeah. Are there any questions? What there are a few.
Hey, thanks for the talk. I was recently reading a lot of papers about centralization issues in DAOs and how most people tend to vote, the rich just get the highest say. Can you speak to that? Can you speak to those issues?
Sure, yes. All right, so we're going to do a lightning talk on that. So first off, I think there's a fundamental issue with thinking of DAOs in terms of voting, right? Voting is a process that's used to render a decision. And by over-indexing on voting the decision-making process rather than on broader notions of steering or guiding an organization, a lot gets lost. So first off, the voting turnouts do tend to be biased in token-based systems because only a relatively small number of people feel as though they can meaningfully affect the outcome. I think there's a relative lack of use of forums and deliberative processes. Although those forums exist, they're often used more to essentially manufacture consent in the Chomsky sense. And that in practice, the movements that we should be looking at are how to better treat the attention of the participants within a DAO as a resource, not necessarily maximizing for participation, but also not necessarily departing from that, rather moving to a set of metrics that are more outcome-oriented with respect to whether DAO members feel as though their interests are being adequately represented, but that's more of a check on the behavior of the DAO rather than a direct metric on participation. And it would be interesting to see how people might implement alternative models that shifted away from trying to get everyone involved in every decision and shifted towards making updates to processes as a function of whether people felt their interests were being represented by the decisions the DAO was rendering.
Great talk. Look forward to digging into the paper. Thank you for sharing the Notion link as well. How do you see in the next few years the evolution of DAOs? In particular, if we see a bull market and prices going up and bringing a lot of people back into the blockchain landscape, what are some objectives or some measurable outcomes that you'd like to see in order to make some tangible progress and continue to evolve?
Yeah, I think tangible metrics. I think I would like to really see more interoperability as opposed to scale. So I don't know that a bull market will help this very much because it tends to make individual organizations balloon, brings in a lot of money, and they try to take on bigger projects that they're maybe not really that well equipped to manage. And so my take is that what makes DAOs so exciting is that they can be fundamentally more localized, more specific. And so they can be smaller, they can be capitalized and orchestrated by smaller groups of people who are aligned in what they're doing. But in order to manage more complex tasks, you would look to DAOs collaborating with each other. And there's a citation in the larger paper to a short bit of work I did a few years ago on DAO-to-DAO protocols. And I think that there's more emerging there. We start to see it through contracts referencing other contracts. We start to see it through organizations collaborating directly and sharing funds in streaming pools, sort of splits types contracts. And the infrastructure is starting to bubble up, but what I'd really like to see is empirical evidence through the data from those contract patterns that the organizations themselves are staying smaller and more specialized, but webbing together into groups that can drive larger outcomes. Just trying to accomplish really big outcomes from these large foundations running these blockchain networks right now. I mean, folks like Optimism and Arbitrum are working really hard to build out grant programs, but the shapes that these programs are taking are increasingly similar to legacy government institutions out of necessity because they're trying to appropriate public funds and they're trying to deliver it legitimately to actors and monitor and validate outcomes. And it moves pretty far away from the sort of underlying open source development pattern. And I think there's some stuff in the middle. And I think DAOs are going to help us find that stuff in the middle.
Hi, yeah, thanks for the talk. And continuing what you were saying about voting, I think like there's additional hardships when it comes to DAOs that are implemented via smart contracts and code, in the sense that it's both technically complicated for end users to understand and comprehend, and also the incentives for voting and participation are kind of misaligned a lot of the time, and I feel like the science behind it is, like when you look at literature, it's mostly like negative results for deciding things that work. So I was wondering if you have anything in mind for that.
Yeah, so I think, and I started to allude to this before, I think that we just haven't scoped the problem right. Like we're asking what kind of voting we should be doing, not what things should we be voting for, who should be engaged in that decision-making process, what other processes go alongside those voting processes to ensure that we're even like considering the right topics. And I have a forthcoming paper with Nathan Schneider, Ronan Tamari, and Kelsey Nabin on attention economies, in particular with case studies around DAOs. And the thing that we highlighted is that the real resource here is attention, and that also starts to invite some of the HCI questions. You're like, well, if I make it really difficult for you to understand the decision-making context, if I demand that you participate in a decision, hopefully in an informed way on a regular basis, I'm not necessarily efficiently using that attention resource. And while we want to maintain representativeness, participatory systems, we want to make sure these systems are as permissionless as possible, at the end of the day, if we don't rescope the question to be a little bit more about making the return on attention for the DAO participants something that they're willing to do, then I don't think we're going to get the kind of growth in the DAO sector that I was hoping for in the previous response.
Yeah, also, if decisions were made in like natural language and then the translation to code was made via a trusted party or something like that. Yeah.
Yeah, so I've been doing some experimentation with MetaGov around co-governing some digital infrastructure, including RAG chatbots, and that's largely been off-chain, right? It doesn't make sense to try to regulate those configurations on-chain, but there's this need for this large community of researchers. I think I mentioned MetaGov is a kind of skunkworks community, like lots of people with governance backgrounds, but with different experiences, researchers, hackers, founders, et cetera. And the group that's there wants to play with these kinds of questions, and our KOI project, Knowledge Organization Infrastructure, is actually about governing like what data is there, how it was collected, who can use it, which kinds of microservices are incorporated into a local mesh, and even which services can call each other is on the table for the iterations on this tooling. And my feeling is that this kinds of knowledge organization infrastructure is going to be critical for decentralized organizations to lower attention costs, but it's a few clicks into the future. I would imagine needing to get to a point where those patterns were sufficiently standardized, to some extent verifiable, and we would have to maintain on-chain records of things like the wiring and permissioning rules. I had some chats about this with Jake Hartnell, who was one of the founders of DAO as well, and one of the co-authors of this paper about storing KOI configurations in the sort of struct inside of a DAO. But that would, at this point, be a hackathon project, right? It's not really the current state of the art.
Time for one final question.
Yes, thank you. Thank you very much for the interesting talk. So, if you were to set up a DAO yourself or design a DAO, what would be some objectives and maybe even measurable objectives that you would optimize for?
Yeah, so for me, like viability, kind of survivability is the ultimate objective. I think one thing that's been interesting about DAOs is they've been pretty short-lived in some ways because they have a balloon of attention often correlated with money and then a diffusion of that attention as it bleeds out into other places. So the metrics that I would imagine focusing on are actually long-livedness, and that would mean probably spending a lot less money. It would probably mean not even necessarily raising as much money, but emphasizing the type of participation that's invited and the correspondence of that participation to delivered benefits, not necessarily financial. That hinges on experience working on SourceCred. I'm not sure if people are familiar with this project. It was funded largely by Protocol Labs a couple years ago, and it involved the instrumentation of a bunch of Git repos and forums and measurement of contribution scores. And those scores ended up becoming the driver of compensation, and the organization lasted for actually quite a few years. The code base lives on and people do still use it. So I look to that example most readily as something that was probing in the direction that I would want to go, but my feeling, and this relates to the kind of constitutionality here, is that that community sort of turned over in people, which is fine, but the later groups of people didn't have the same level of comfort with the infrastructure, and so they weren't able to adapt it to meet their own needs. So the breakdown potentially could be attributed to the loss of the sense of autonomy, because it felt like the algorithms were controlling the contributors rather than the contributors actually controlling the algorithms, and I understand that as a kind of dance. And if you're interested in that work, there's a long-form ethnography of SourceCred by one of the other co-authors from DAO Science, Ellie Rennie.
Interesting, thanks.
Unfortunately, we are out of time for this session, but please feel free to talk to the speaker afterwards. Let's thank the speaker again. And our second and the last speaker of this session is Jeff Burgess. He's a senior researcher in cryptography and distributed systems at Web3 Foundation, and he'll be talking about efficient block auditing for blockchains. Please take it away.
Hello, I'm Jeff. Well, I guess we have to wait for this thing. Yeah, Polkadot. I'm speaking about the protocol that's been used in Polkadot for sharding since 2021. Polkadot also has an interesting DAO problem, so I'll make people read his paper. Okay, so this paper is ePrint, the crypto ePrint 2024 961. So there's a lot of co-authors because we had a lot of people involved, including implementers. It was originally sort of me and Alistair and Rob Habermeyer who worked through the design of it, but it takes a lot of people to maintain something like what I'm going to show you. Okay, so all of Web 2 requires sharding. So this meaning horizontal data partitioning. I mean, real services grow, and there's no way you can do it with one machine. Blockchains simulate a database through auditing. This is fundamentally what they do. The machines audit the updates. But that, they're basically simulating a single threaded database. It's kind of shitty. So are they only for these toy services that we're using them for now, or can we actually make them scale up to run real things? So what that means is, one of the things that means is we have to make the auditing more efficient. Okay, so block auditing protocols just means how the blockchain checks blocks or checks the blocks of other chains or whatever, things like this. So the questions you have to ask, one question is it provably secure and under what assumptions? And how much does it cost in computation, bandwidth, opportunity costs on the nodes, and energy? So at least the first two of these, we can actually, as a kind of a course reference, we can just say costs in terms of number of machines is actually a reasonable metric. Of course, it's more nuanced than that. There's other protocols, other questions I'm not going to be talking about here, like censorship resistance, liveness, and the machine storage. Okay, so a simple example of a block auditing protocol is a bridge. So you have a bunch of blockchains and they're all bridged together. The basic disadvantage of this is as you add more blockchains bridged together, then you're still assuming 2/3 honest on each of them, so the protocol security will drop if you're interacting with a bunch of them. So eventually we should see the bridge ecosystems have very interesting attacks that involve a human element and other things. Another one is these optimistic rollups. Generally, these things are not provably secure, or if somebody does manage to do a security proof, it will probably involve a lot of wild assumptions, like not explaining why validations are happening. Because they have this problem, they generally have some kind of inter-shard latency which is of like a week, or at least the current big ones do. So that's also kind of shitty. You don't want your sharded database to need a week of latency between shards. So a more serious thing is these ZK rollups. So we have a succinct-ish cryptographic proof for each block. These are great because they have very weak assumptions. Exactly what depends on what you're doing. Like Mina would be, if it's verifying the ancestry like Mina, then that changes your Byzantine assumption, improves your Byzantine assumptions even. This is cool because they're recursive, very composable, very good, but they're very expensive. So just quoting Justin Thaler, that generally they're 1 million to 100 million times the cost of a single verifier in terms of CPU time. So we're interested in total CPU time, like the actual costs, not just the on-chain CPU time. So those numbers are not the end of the story. If you're Ethereum and you're paying 500,000 or 1 million nodes, that's great. You save 1 million times the bandwidth. But anyway, some of these things are ending up with inter-shard latency of like an hour, and this will worsen MEV. That's still a problem, and there will be very high opportunity costs because of the need to be able to do all this computation. And also, a lot of the assertions that these things will improve are like using specialized hardware. Of course, anybody can use specialized hardware. It's not unique to them. There's nothing special there. So the real question is about the algorithms. So what we're going to be talking about is transparent verification. And if ZK things can improve that, great. But okay, so true sharding, this is not what we do. Eventually, everybody will be doing this. There's a paper on it by Brian Ford's group at EPFL. The way it works is you take a very large set of validators, you assume you assume some higher honesty threshold, like 80% honest, and then you put like 1,000 validators on each shard, on each chain. And then you use some kind of concentration inequality like Hofding or Chebyshev to argue that you have 2/3 honest on each of those chains with very high probability. Concentration inequalities prove that things group towards the mean a bit. Okay. So what's cool about these things is that they can do everything. Like the entire distributed system can be put into this kind of sharding. So you can be running all kinds of off-chain protocols, and so they're kind of magic. They're much better than ZK rollups at the distributed system side. Intershard latency can be seconds or minutes, but it happens after sort of finality from the different shards. So your bridges are fast within this large set of validators. The bridges are fast and trustworthy. They don't really have any other disadvantages other than the sorry, I missed the first line here. So of course the advantage is that it's 1,000 times cheaper than a ZK rollup in CPU, but it's 1,000 times the bandwidth cost of a single verifier. So like 50 times the bandwidth cost of a ZK rollup. I mean a decentralized one. So we don't need recursion here because of the way the assumptions are working. The other kind of pseudo disadvantage is people think they can do it and they fuck it up. Even the professor coins screw this up. Like Dfinity has 15 to 40 nodes on a shard, and I'm not sure they assign them randomly either. I have no idea. Okay, so I'm going to be talking about the sharding in Polkadot, which eventually we will need this true sharding that I just explained on the previous slide as well. But what we're talking about is sort of sharding for smaller sets of nodes. So I'm going to go through 4 tools that we need. The first is soundness slashing. Slashing is generally pretty evil. Professor coins don't do it. It's also pretty necessary for a lot of Byzantine stuff. So it's what it is. Soundness slashing is not as nasty theoretically as all of the slashing you need from a Byzantine perspective. You simply need, for soundness slashing, you absolutely need a provable violation, and you can't have any sort of gray area, and then you need to know sort of you need to know sort of what's the value you're protecting, and then you can argue your soundness error. So a soundness error of less than 20,000 to the -1 is perfectly fine. So 1 over 20,000 is perfectly fine if you're trying to protect. If you have sort of 5% of the value of the network in stake. Okay, that's in total stake. Okay. Right. So another tool we need, which people probably know about, is we need stateless blocks. This means, so in Polkadot, the blocks are coming from these side chains. We call them parachains. And the parachain has to attach state proofs. So we're doing transparent validation everywhere, so that just means they're attaching Merkle proofs to their blocks, which blows up the size of the block quite a bit. You could do other things. KZG is too slow. Maybe there's some other flavors of KZG which are better. The two last talks on the first day are kind of interesting. Latticefold, maybe if you use some lattice-based hash functions, whatever. But ultimately, we're doing this computation versus bandwidth trade-off, and right now we're pushing on the bandwidth side. Maybe we have to change that eventually, but anyway, all right. So another tool is availability commitments via erasure coding. So the general idea here is that the block body becomes a code word in erasure code, and then it gets chopped up into little chunks. And then you have a Merkle tree that commits to those chunks. And the questions you should ask of an availability protocol are the chunks retrievable, and how do you know that the encoding is correct? So there's the popular one is this 2-dimensional Reed-Solomon. It has a really shitty undecodable ratio of like a quarter. That means a quarter of attackers can hide the thing. So they have to do a lot of sampling, use a lot of bandwidth to deal with that. and then the reason people like it is because they can do these fraud proofs from only a small chunk of the block, but this doesn't matter very much because the validity is not a property of the whole block. Validity is a property of the whole block, not of the transactions. It's useless to see a small part of the block in general. We only care about what a full block does. So not interested in two-dimensional Reed-Solomon. One-dimensional Reed-Solomon, with 1/3 threshold, gives us the attacker must hide 2/3 of the block of the shards to do anything. So in combined with 2/3 honesty assumption, we're great. 2/3 vote yes, 2/3 honesty assumption, we have 1/3 left over, we can reconstruct. So we're putting one chunk per node, which is also different from how the 2D Reed-Solomons work. So the total bandwidth of doing this is about 3 downloads of the full block. This is very efficient. And again, as I said, we're doing all or nothing reconstruction. So whenever we finally check, essentially, as the previous thing was taking a small block and making it larger or as the stateless block is taking a small block and making it larger to make it stateless. Now we're taking the stateless block and we're making it 3 times bigger in a sense and so that it can be distributed in chunks. And so when you check the block, you will have to check these chunks. All right. Now, there's a number of other reasons. I didn't go into this about the Reed-Solomon, but when you want things like batch verification and whatever, this stuff is only efficient when you can check the full block all at once. All right. All right, so let's talk about actually the protocol that we use. So it's kind of you can think of it as a kind of a cut and choose protocol, but under Byzantine assumptions. So we're assuming 2/3 honest, plus we'll be assuming synchrony in one place that I'll get to, and also this soundness slashing. So the parachain makes these stateless blocks, and they passes it to this relay chain, which you can think of as like the beacon chain on Ethereum. There's a few interactions on the relay chain that have to do with availability primarily, but actually a huge amount of the complexity of the protocol is going from the parachain to the relay chain. This turns out to be extremely complicated, and that's going to impact everybody who's doing lots of things. But anyway, because you don't want a mempool, it has to be more efficient than that. Okay, so what happens on the relay chain is some validator declares responsibility, and they do this erasure coding, and they ship out the chunks to everybody else once the relay chain acknowledges that they've declared responsibility for this block. That shipping out the chunks, all the other validators are kind of voting on these bit fields of whose chunks they have received. This gives an efficient proof that that the block will be checkable in the future because we now have all of these pieces. So now, at this point, we have not proved the thing yet, proved these parachain blocks are correct, these parablocks are correct, but somebody's on the hook for them, and we know they can be checked. So we're just going to go ahead and optimistically send all the messages. So this gives us inter-shard latency of tens of seconds. All right. What happens now? The nasty part. So what's going to happen is there's this kind of approval gadget, which I'll explain in a second, and the validators are self-assigning using verifiable random functions on what they're going to check of the incoming parachain blocks. And basically, we just delay finality until everything is approved. So the entire validation process, the actual validation process, is basically a delay on finality, or causes a delay on finality. If anybody disputes in this process, we escalate and everybody checks, and we just make that economically viable. And if any of the disputes pass, if any of the disputes conclude that the block was invalid, then we just kill the backer, the guy who originally is on the hook for it. So that's basically a $2 million fine. Okay, so the advantages of this protocol, like I said, inter-shard latency of sort of tens of seconds. We only need about 30 to 35 checks. Actually, it's probably a little high. It's probably about 26 to 30, low 30s. So this makes it about 29 times cheaper than than the true sharding. And we probably will get this down further with some protocol changes. So it's going to be really hard to beat this in terms of total CPU time. And we basically will prove security by exhausting the stake under an attack. So another advantage, this whole protocol was designed to pipeline and batch very well. Disadvantage, you need all that pipelining and batching to make it efficient. It's of course complicated, going to be complicated, and this soundness slashing is nasty. And as I said, there's going to be a synchrony assumption in here. And the other thing is this thing, I've been talking about scalability. Alone, this thing is not really scalable because gossip isn't scalable and we need gossip. So in the end, what this protocol does is it scales us up to a sort of 1,000 validators while having only about 30 check each thing, and then you have to use true sharding and assume 80% honest beyond that. But we haven't done that yet. Okay. So okay, so first, what does one of these auditing tasks actually look like? So the first thing that happens is there's a local VRF that tells each validator, each node, who they're supposed to be, which things they're supposed to be checking. I'll talk about those on the next slide. And they have to announce these. This is the place where we're assuming synchrony because we need people to know who's supposed to check what. But then after they do this, they reconstruct, and so in the synchrony, sorry, one more comment about the synchrony assumption. We're sort of willing to do anything here to enforce synchrony, like use specific UDP packets or various other things. But we can get this into sort of a single packet. Okay, so the rest of the auditing task is you reconstruct from availability, you re-encode to check the erasure routes. This is checking the erasure coding, the original erasure coding, and then you actually check the block itself and announce the results. So that's what an auditing task looks like. And now how do we decide what happens? So who's doing what? So there's two VRF conditions that decide what people are going to be auditing. The first one, we call it tranche 0. It sort of samples widely across all of the incoming parachain blocks. And the important thing here is that the number of samples each validator uses is supposed to be this the number of checks we want, the base number of checks we want on each one of these things. That times the number of validators is supposed to be the base number of checks times the number of cores or the number of tasks that we're trying to simulate or that we're trying to run. So after this happens, there are other tranches that can check. And what happens is if the validators just sort of sample kind of a delay, we call it this tranche number, and everybody is assigned to check everything at some delay. And what will happen is they'll only be triggered to check by somebody who announced that they're going to check something failing to do so. Basically, if somebody doesn't check for 12, if we don't get any response from a validator for 12 seconds, then whatever work they were doing will get checked by 2.25 other guys in expectation. So, okay, now that 2.25 means that if you have a 1/3 adversary, then you're checking by, in expectation, 1.5 honest guys. And the point is, eventually every validator either approves disputes or becomes one of these no-shows. All right, so why 2.25? We wouldn't want to have 1.5 or less because then the number of honest checkers would only be 1, and in principle the adversary can exhaust it. We wouldn't really want to have more than 3 either because then it would take a relatively small number of malicious nodes to cause, or just nodes going offline to cause some disputes. And you can look, this is some computations from the paper on sort of final committee sizes. Based on the size of this F delta or yeah. All right. So that was So that was one important thing, is the size of these non-zero these tranches after 0. How big do they have to be? the other question is how big does this first tranche of checkers have to be? And the computation for the paper looks like this, just doing some probability theory to come up with this. But it depends, so gamma's the proportion of dishonest nodes. So it depends on this soundness error, and also on the proportion of dishonest nodes, and then on the and it depends as well on this how many we're signing per later tranche. Originally we just worked out this number 30 here using simulations. I guess the number is really 26, but because the simulation code wasn't that great in some ways. But right. So here's sort of a graph of the trade-off between the size of the initial committee and how big of a size of the later tranches to still be able to prove security. So we're currently up in the epsilon Polkadot's working. The epsilon Polkadot's working with at the moment is something like 100,000, not just the 20,000. So we're well into this safe range. All right, so some other things I want to, so what is actually something about the real performance? So we're running something like 6-second block times on the relay chain. Parachains can run faster via what's called elastic scaling. So this means that the parachain can make blocks in multiple sort of core slots of the relay chain, and the relay chain will just check that they chain together. This means, at the moment we don't let them go that fast, but they can go pretty fast if they want to. The parachain blocks are 5 megabytes and have about 2 seconds of single-threaded WASM. There's a RISC-V byte code we're working on called PolkaVM that will be better than WASM for this. As I said before, we've been running this since 2021, slowly improving the bottlenecks. Currently, this Kusama network has about 100 parachain slots on 1,000 validators, but we'll definitely get it to 200 next year. So that means we'll be running about 1 blockchain for every 5 validators, and we'll probably get it to 1 every 3. How much more than that, I don't know. One of the major things here, one of the major constraints is so we can force upgrades of software. That's the only way we're able to build the system, is being able to actually do upgrades. But we can't really force our upgrades of hardware yet, so a lot of the nodes are too weak. The recommended node size was only 4 CPU cores. That needs to be improved, and we have a lot of assets who run like 2 cores. So we're getting a lot of performance out of some relatively shitty machines. That will be improved. We have a protocol that will tie the rewards more closely to what people are actually doing. It, again, also runs off-chain. So some observations. This protocol gains dramatically from being run off-chain. If you wanted to try and make an SZK, roll up off of this, it would be nasty. The small per block committees that we get may be useless without this soundness slashing. These no-shows that I was talking about, they happen. We get about half a no-show to a no-show per block, depending on what kind of upgrades we've done recently. That just happens. It's fine. We've only had a few escalations, but generally they were our fault, so you need a DAO to be able to reimburse people when things go wrong. So the system depends on being able to have a DAO. An anti-upgrade ideology would have made all of this impossible. And there's a bunch of complexity that I've hidden under the rug in this talk. As I mentioned, that the flow between, just between chains is actually really nasty to do correctly. Generally this protocol has required a lot of benchmarking and figuring out what needed to be worked on to get it where it is. I think that's all I want to talk about, so I'll just take questions.
Okay, thanks for the great talk. Are there any questions from the audience? Okay, while people are thinking, I actually have a question. Could you go back to the equations line before the graph?
This?
Yeah, is this W0 the Lambert W function?
Yeah.
Okay.
Yeah, because when you're doing the computation, it's the correct branch of this thing, because the other branch would give you the same thing, the input back out, and you don't, well, yeah, anyway. This is in the paper, the arguments for it.
Yeah, I was actually skimming through the paper and realized you guys have a parallel contribution on strengthening Cantelli's lemma. A parallel contribution on strengthening Cantelli's lemma, I think.
Parallel?
Like you were strengthening an inequality in probability theory, Cantelli's lemma.
Okay, yeah. I mean, so our Alistair Stewart is very much a real, like his PhD was in robust statistics and did very interesting work there before coming here.
Yeah.
Yeah, so the probabilities don't scare us.
Great. Yes, there's a question.
I was wondering if you had any way to address essentially the lazy validators problem, the notion
so that's essentially what I was talking about. Here, that we sort of created our own lazy validators problem, because when the first system was initially designed, so Gavin originally designed what was basically an optimistic rollup. This was Alistair Stewart and Rob Habermeyer and me, and then all these other people that on the Parachain team and the research team that changed it to be this way. So originally, when they were first making specs for substrate, they were just like, oh, we need fast single-threaded performance, but we don't care about cores. So we put down recommended 4 cores, and we have a problem that people run only 2. So even if they're not lazy, like intentionally lazy like you're thinking, we already have a lazy problem that they may just fail to check and cause no-shows, and other people will work. So the answer, I didn't talk about it at all in this talk, is this. So part of it will be this reward system, and we're also very careful about this. So I didn't talk about this either, but we have slashing that happens. So if you cause a dispute or an escalation, because remember, this system will escalate on its own even if there's no dispute. Like if people just aren't checking. If you cause that, you will eventually get slashed.
So presumably a malicious lazy validator could say that they checked the block, thus they wouldn't
Sure.
qualify as a no-show.
So yeah, there's nothing we can really do about. So an important thing to remember there is that there aren't that many other people checking it. Yes. So this is definitely a risk. They're risking a great deal of money. It's the only real answer there. Another part of our system. It makes that more risky, which is this NBUS thing, which what it does is so in the system all validators are effectively equally staked, because we solve this voting theory problem to try and assign stakers to validators, but yeah. I would say the real problem there is less the specific lazy validator problem that you're thinking. Is that the nominators, the people whose stake is being applied to the validators, aren't actually checking. So in the same sense as Tor has to have meetups where they like teach validator, Tor node operators things like how to talk to cops and whatever, we really need to have meetups between nominators and validators to try and maximize the chances that the nominators actually know the people they're nominating. And the whole view of, in my personal opinion, is the whole view of thinking of staking as this financial thing is a disaster from the security perspective. Yes, we do have that problem. The only real answer is that you lose a lot of money.
Thanks.
And we have to keep the rewards high to make sure that,
Right, let's thank the speaker again. This concludes the session. There must be lunch outside. Thanks for the talk. Yeah, thanks. Great talk.
Hello. Hello, everyone. Welcome to the after lunch session of Friday. The next session is on Consensus 2. And for the first speaker today, we have my dear friend and colleague from Stanford, Joachim Noy, who is going to speak about optimal flexible consensus and its application to Ethereum. Thank you. Stage yours.
Thank you. All right, good afternoon, everyone. It's great to be here again. Let's see, this works? Okay, perfect. Welcome to the talk. This is a great piece of work that I'm very happy with because it's one of these rare moments where we get to do interesting theory and at the same time stuff that is fairly practically relevant. So I'm very excited to share these results with you. So yeah, my name is Joachim Noy. I did my PhD at Stanford. Now I'm with A16Z Crypto Research, and this is joint work with my colleagues Srivatsan, Lei, and our advisor David. And the paper for this talk that I'm about to present appeared in Oakland earlier this year, and if you want to know more, find the paper on ePrint, and we also have an ETH Research post that I'll reference later on. Before I get started, I have to give you important disclosures. And let's move on. Okay, so we want to talk about consensus. In consensus, we have a bunch of validators that receive transactions from the network. This is basically your blockchain network, if you will. And their job is to determine an ordering of these transactions so that clients later on can recover a log, an ordering of these transactions, which they can then feed into the execution engine of their blockchain, basically, right? So if we design consensus protocols, what properties do we want these protocols to have? There are typically two. One is what we call liveness, which is that if somebody sends a transaction to this network, then eventually this transaction should sort of be dealt with by the network and should sort of be sequenced and appeared in the output log of all of these clients. And the other property is safety, which is that throughout time, for any two clients, K and K prime, their output logs should be consistent. So one log should be a prefix of the other. They should not have disagreement about which transaction comes before which other transaction. Okay. Why is this hard? This is hard because this all happens on the internet, and the internet is far from a perfect place, right? Whenever validators send each other messages, there's network delay. Sometimes the network delay could be really bad, in which case we call this a network partition. And some of these validators may not be following the protocol, okay? So we assume there is some fraction f that may be malicious and may be trying to stop our protocol from reaching consensus, okay? So the expert among you have now recognized we're here in the partially synchronous or eventually synchronous network model. And so we cannot hope to solve this consensus problem like all the time. We can only solve it under certain conditions on the network, but in particular also on the adversary strength. Okay, so we introduced two parameters. One is called liveness resilience, TL, and the other one is called safety resilience, TS. So now our consensus problem is parameterized in this tuple. And we want to ensure liveness whenever the adversary fraction is less than the liveness resilience. And we want to ensure safety whenever the adversary fraction is less than the safety resilience. Okay? Now we can ask, okay, fine. I have this problem, this consensus problem now, which is parameterized in these two numbers here. For which tuples do we actually have protocols that solve this problem under partial synchrony? Right? So now we can plot a region, basically, of liveness and safety resiliences. And we can explore which points, sort of in this two-dimensional space, for which points is this consensus problem actually solvable. Okay? And there's a very famous impossibility result going back to 1988, which basically gives us a region in this two-dimensional coordinate system for which we know for sure that under partial synchrony, we cannot reach consensus for those points. Okay, clearly we would like to be, as up top right as possible, but there is a certain region where we cannot go. Okay, so what about the other points? There's a second region, which is a region where the liveness resilience is greater than the safety resilience. So that's sort of a strange region because if we have a consensus protocol for that region, you know, there are certain points, certain adversary strengths where we can guarantee that transactions are being confirmed, but they could be jumping around in the output log, right? So it's not so clear what to do with this. So usually, you know, we're not so interested in operating in that region either. Okay, so that leaves us with this blank triangle, and you know, we want to be on the top right, right? And the traditional parameterization that you find in classic consensus is we try to operate at this you know, corner point here that is 1/3, 1/3, right? This is the point that sort of maximizes the minimum of the liveness and safety resilience. Okay, so this is what protocols classically do, right? But now, you know, these are blockchains, right? They're very heterogeneous clients. You know, some clients, they differ a lot in terms of the workload that they put onto the system, right? And maybe you have some clients, such as these Alice clients, that are running some sort of an exchange, and they're more concerned about safety than about liveness, right? Because safety for them means, you know, if there is a safety violation, it means there could be a deposit that is being reverted, right? Where maybe they have already authorized the withdrawal of the money. So that would be catastrophic. Whereas on the other hand, you know, if there's no liveness, it basically means, okay, there is a point in time where they cannot accept deposits right now, right? Which is maybe okay. So these exchanges, you know, they may be trying to say, okay, given, you know, this kind of triangle here, right? We want to be at the top right. Why don't we go to this, like, you know, somewhere closer to this point here with very high safety resilience, possibly kind of trading off a little bit of the liveness resilience, right? And on the other hand, there are, you know, the Bobs in the system here who are like, no, like both of these properties are important to me, and you know, the classic trade-off is 1/3, 1/3. Let's keep it that way, right? Let's not compromise the liveness too much. You know, this is about censorship resistance or something, right? And so now you can ask the question, okay, you know, to what extent is it possible to satisfy both of these requirements simultaneously, right? And that is what we do in this problem called flexible consensus. Okay, so now I'm going to change the problem, right? From this problem, I'm going to introduce a few more parameters, right? We're going to say, okay, every client now comes with their own safety liveness resilience pair, right? The Alice clients want to be, you know, very high safety, compromising liveness, and the Bob clients want to have 1/3, 1/3 safety liveness resilience. And our flexible consensus problem is now parameterized in a whole bunch of these safety liveness resilience pairs, right? One for every client. Okay, and we want to guarantee liveness. We want to guarantee the consensus properties for all clients that have made a reasonable assumption about the adversary, right? So if a client assumes a liveness resilience that is actually higher than the adversary fraction, we want that client to have liveness. And if two clients, K and K prime, have assumed safety resiliences that are actually greater than the adversary fraction, then we want these two clients to be consistent. Okay, that's the flexible consensus problem. And now again, we can ask, you know, which of these trade-off points here, right? For which of these parameters is this problem actually solvable? Okay? And the first, so we're looking at flexibility of protocols, and the first observation is, well, if we have a protocol that gives 1/3, 1/3 to every client, right, that is also a flexible protocol, but it's just a very trivial one, right? It's like basically allows like one point in that trade-off space. Okay? So classic protocols that are parameterized at 1/3, 1/3, right, they're also flexible protocols in some sense, but sort of they have no flexibility, right? So these protocols, you know, in that particular case, that's great for Bob, not so great for Alice. But then in these protocols, you know, if you're a bit familiar with them, we can tune the quorum and move this kind of trade-off point kind of further into a region that Alice likes. Then the protocol becomes good for Alice, but now, you know, Bob is no longer happy. But the bottom line is, however you parameterize these protocols, all clients are operating at the same trade-off point, and so you get no flexibility. Now, this problem of flexible consensus has been studied before, like a few years prior, in works called FBFT and SFT. And they give flexible consensus protocols. And in fact, as far as I know, the first kind of non-trivial flexible consensus protocol. In the following sense, they allow clients to choose points simultaneously, like on a line, right? No longer on just a set. Okay, so if you take that protocol, for example, Bob can choose to operate, to tune his output log in such a way that he obtains 1/3, 1/3 liveness and safety, and Alice can increase her safety resilience by compromising her liveness resilience up to 2/3 safety resilience. Okay, now there is a non-trivial trade-off, and again, this got a little better for Alice, and again, there's an internal kind of quorum parameter that you can tune, and if you do that, you shift that line sort of up, and it becomes better for Alice and not so good for Bob anymore. Okay, so there's some flexibility in these protocols, but the question that wasn't asked is, what's the maximum flexibility that a protocol can provide and how, right? If you go back to this idea, right, we want to be at the top right of this plot, right? Ideally, right, we would like to be able to, be on that full trade-off curve here simultaneously, right? And that's exactly what we do in this work. We present these OFlex protocols, which stands for optimal flexible, which do exactly this. So they allow a trade-off where, which is the optimal flexibility trade-off, where both Bob can operate at 1/3, 1/3, and Alice can operate at safety resilience 1, liveness resilience 0, and they're sort of, they're not forced into a mutual trade-off. Okay? So we get a theorem that indeed, right, we achieve that full, kind of Pareto front of points that you may want to be on. Now the question you should ask is, why is this possible? Right? I would argue that this is kind of unintuitive that we can do this, right? Because we're used to in life that, if you have two kind of conflicting goals, usually you need to compromise, right? If you talk to two people and one person speaks English and the other person speaks German, you usually have to choose whether you want to speak German or you want to speak English or you want to speak something somewhere in between. And if you speak German, the German person understands and the English-speaking person not. And if you're somewhere in the middle, right, then you only get like half of the information across, right? So that's how it typically goes in life, right? And here it's somehow strange because I seem to be saying, oh, actually, we get both a system that is like, as good for Bob as if we had built the system only for Bob, and as good for Alice as if we had built the system only for Alice. There seems to be no trade-off. Why? Right? And in order to understand that a little, I want to look at this example of like, the two extreme points, right? A system, suppose we only had an Alice and a Bob client, right? Can we build a system for these two users? And the key observation, why it turns out we can build systems that sort of fit both of these users simultaneously, is that their requirements are degraded. They're degraded in the following sense. Whenever Alice requires liveness, then Bob also requires liveness, because Alice's liveness resilience is lower than Bob's liveness resilience. And whenever Bob requires safety, then Alice also requires safety, because Alice's safety resilience is greater than Bob's safety resilience. And that gives us an idea how we could construct a system like this, right? We start with a protocol that is tuned for Bob, 1/3, like a 2/3 quorum, just a traditional protocol. All the validators run this protocol, right? And the output of the protocol is what Bob uses as his output log. But then we add a second protocol into the mix, a protocol that is also being run. So all validators run both protocols simultaneously. This is a protocol that is tuned for Alice's safety and liveness resilience. And Alice is going to use the output of that protocol, but the input of that protocol is no longer, just transactions. It's only sort of logs that are already confirmed by the first stage protocol. Okay, now what you get is that clearly Bob's safety and liveness resilience just comes from the safety and liveness resilience of the first protocol. So that's great. Bob definitely gets the properties that he wants, right? But to understand what's going on for Alice, we need to use these properties, right? So if we want to see safety for Alice, right, that's fine, because the safety for Alice is just dominated by the safety of this protocol here. Okay, so the safety for Alice is whatever this protocol, the safety resilience this protocol has, and so Alice gets the right safety resilience. In order to understand why Alice's output log is live, we have to use the fact that whenever Alice can expect liveness or wants to have liveness, we know that Bob also requires liveness. And because of this, we know that this protocol is live. And so the very fact that we have put this protocol in front of this protocol sort of doesn't stop the liveness of that second stage. Okay, and then the last property we need to check is that if Alice and Bob's assumptions are satisfied simultaneously, right, then both of them need to be consistent. But then what's the case? Well, if both of their assumptions are correct, then in particular Bob requires safety, right? And then the first stage protocol is safe, and then whatever Alice, like the second stage protocol confirms, will be consistent across Alice and Bob, right? And that's basically the high-level proof sketch for why this construction works. Now you can say, okay, now we go from here, right? This works for 2 clients. What if we have a third client, Carol, somewhere in between? Well, still these kind of relations, these degradedness relations hold. And so, you can just add a stage here in between, right? And then the whole same argument kind of goes through. Now you say, oh my God, right, if I have many, many clients and I need to add many, many stages, everything's going to be awfully slow. That's not really a practical solution. That's true. There is another insight, which is that these higher stages, everything other than the first stage, you don't actually need full-on consensus. There's a sort of, you can open these boxes, do a bunch of optimization, and what you end up with is a very simple construction where you just run a protocol, a one-third protocol, and then a simple kind of extra logic step, an extra round of voting and an extra locking mechanism. And the way this works is pretty simple. It's as follows, right? The first protocol outputs a log, and whenever that log grows, in the second stage protocol, validators are going to lock on the input that comes out of the first stage, and they're going to cast a vote for that output log that came out of the first protocol. And then if the first stage protocol is unsafe and it outputs something inconsistent with their locks, then they will no longer update their locks and they will not vote for this. And then you go with these like extra votes, these post votes that we've just added, and Alice and Carol and Bob and whoever else there is, based on their safety, liveness, resilience that they've chosen, they will choose a local confirmation quorum that they will apply to these extra round of votes. Okay? And there you go. So, just recapping, this is kind of the construction, right? There's the validators run everything up to the confirmation quorums. The clients then run the confirmation quorums. And you can now ask, okay, there's 3 things that we're adding, right? Post votes, permalog, and confirmation rule. Where do we get them from, right? 2 of them are validator logic, the other one is client logic. So I've shown you that, for any classic protocol, for any protocol that you can use here, if you just add this stuff on top, you get an optimal flexible consensus protocol sort of in a closed box transformation. This works with DAG-based protocols, whatever protocol you have. Then if you have one of these pipeline protocols, like Hot Stuff, Tandem, in Casper FFG, or Streamlit, you get this extra round of voting basically for free because you can pipeline it into the existing votes that the protocol already has. All you have to add is this perma-lock, which is like a small if statement, and these client confirmation quorums. So you get this, for those protocols, you get optimal flexibility with no additional messages. And then finally, many of the implementations we have found, including Ethereum, already has a performance optimization that effectively implements this additional if statement that you need. So in those cases, you can get optimal flexibility with no system-wide changes. You only need to change the confirmation rule, kind of the wallet side or full node side logic. So clients can unilaterally adopt optimal flexibility in Ethereum, and in fact, we built a prototype of what that would look like. I'll show you here the plot sort of during the Shanghai hard fork in April of last year, where the participation in the network becomes a little unstable because of the software update. And we look at the output log that is being produced both by the native Casper confirmation rule as well as these OFLEX rules that have increasing safety levels. Okay? And then what you will see, I'm plotting here, over time, the output ledger length. What you see is that if you have a relatively low safety resilience, right, then everything kind of proceeds as before. But if you go for slightly higher safety resiliences, then because of this drop in participation, some of these output logs will be stalled temporarily. Okay, while the participation is low, there are not enough votes to basically confirm blocks anymore. And so for a short time, you know, the output logs will not confirm any new transactions. And then once the participation heals, the output logs catch up again. Okay, if you want to know more about this, then you can check out our ETH Research forum post. In the context of Ethereum, you know, we call this a super finality because it basically gives you a notion of confirmation that gives you higher safety than what you can expect from Ethereum's finality today. And then I want to just close with a few, you know, last thoughts. One is that, you know, keep in mind, you can run this confirmation rule basically on a per transaction basis, right? So you would probably not want to run this confirmation rule for like every transaction that you ever do, but you know, if you have particularly high value transactions that you really don't want to have reversed, then you may want to opt for higher safety, and then these confirmation rules may be useful to you. The other thing is that this also applies to L2s, right? So if you think of like rollups with a decentralized sequencer or sidechains, then what we typically think of is sort of kind of L2 finality using 30% or based on 2/3 of L2 stake, and we think of L1 finality based on 2/3 of L1 stake. And now with Oflex, what we get is additional sort of trade-offs where we can opt for higher safety, both on the base layer up to 99% L1 stake, but also on L2. So that gives us in particular something that is sort of you know, more safe than just L2, traditional L2 finality, but still, you know, maybe less safe but faster than what you would get with L1 finality. If you want to know more, check out the paper. And if any of this you know, is interesting to you, please don't hesitate to reach out. We're very happy to you know, talk more about it, explain more you know, how this works, etc. And you know, how it may apply to the protocols that you're interested in. And I'm happy to answer any questions.
We have time for several questions. Let's start with Orpheus.
Thanks a lot for the brilliant talk. So this trade-off seems to be, it reminds me a lot of what happens when in a Nakamoto-based consensus, I just wait for longer. Is there any insight into the relation with that and whether I get the same kind of guarantees if I just wait longer in Bitcoin or Ouroboros or wherever?
Yeah, very good. That's correct. I think the intuition is correct. You know, in Nakamoto's consensus protocol, whether it's proof of work or proof of stake, right, we have this k-deep confirmation parameter. And if we have small k, then we see output logs that are sort of faster, but have a higher error probability or reversion probability. And if we use larger k, then we see lower reversion probability, but also increased latency. And so there's a similar trade-off there. It's not here. It's a trade-off sort of between speed, essentially. So in Oflex, there's not really a trade-off on speed. And on reversion probability, it's a trade-off more on like resilience. In Nakamoto consensus, there's no trade-off on resilience. There's only a trade-off sort of the reversion error probability and the confirmation speed. But I would very much say, yes, this is also flexible consensus in that sense.
Great, thanks.
Okay, thank you. This is a really cool idea. I just wasn't clear on one part. So if you have like one party that has lower safety threshold than the other party, in a practical sense, it seems to me like these could end up in like a divergent chain. So because people vote within like a certain time span, and if you don't get enough for the higher safety threshold, it's possible that the lower safety threshold keeps building on blocks and then the other one kind of gets stuck. But and I guess my key insight is like, how does this work in this partial synchrony solution where you're assuming that votes are going to come in within like a specific time?
Yes, very good. So the thing that's important to keep in mind is these quorums are not quorums that are applied by the validators. Okay, so in these protocols, we typically have a 2/3 quorum for something like notarization or something. You only proceed if you see 2/3 votes. Those ones we don't change because in this picture here, those are the votes that sort of correspond to the first stage, right? And that's still just a 1/3, 1/3 protocol. What we change is sort of the quorums that clients use to do confirmation.
Okay, I see.
So what can happen, this is a correct intuition though, what can happen is that clients disagree whether a transaction is confirmed or not, right? At least temporarily while there are crash faults or something, right? If it turns out that the reason this wasn't confirmed is because there were a bunch of crashes and the crashes eventually recover and there'll be enough votes again, then the clients will agree again. If they continue to disagree, then they should look into this anyway. But then it's definitely the right thing to do is to kind of go with the more safe client, right? So the less safe client is basically the one that doesn't know whether the reason for this is like inconsistency or something like that.
All right, thank you.
So the theoretical minimum latency for consensus is something like 3 message sends. And the post vote presumably adds another message send to latency. It's a message send that sort of would have happened anyway in a pipeline protocol, but it adds more latency before, as a client, you can make a decision. Is this something that's fundamental to a protocol like OFLEX, or might we see some version in the future that brings down minimum latency?
That is a very good question. I do not have an answer to it. So we do not have a protocol that, so the question you're asking is basically, do we actually need that extra round of votes, or is it easier, is it possible to do without? And I don't have an answer to that, yeah. We don't have a protocol right now that can do this.
Okay, I can also ask one question, I guess. It seems that these protocols are about quorum-based constructions. They assume a particular population, right? It's one of these variants of final and accountable protocols. But what about the available protocols? Do we also have liveness resilience versus safety resilience balancing there? And can we make these things?
Good question. You're thinking of protocols like Nakamoto consensus?
Yes.
I think it's a question that is worth asking. I don't have an answer to it. So I don't know if, I don't think that has been done. I don't know if it's possible. I would expect that it's possible. But yeah, we haven't done it.
Let's thank Joachim again. The next speaker of the session is Surav. He will speak about asynchronous consensus without trusted setup or public key cryptography. So Surav is coming from UIUC. The stage is yours.
Okay. Hi. Yeah. Thank you all for coming. I'll talk about our paper, Asynchronous Consensus Without Trusted Setup or Public Key Cryptography. This is a joint work with Cici, Shengxi, Atsuki, Lingren, and Victor Shu, who is also around. Let's get started. So you're in the consensus session, so we will start with the classic consensus problem. And this is an n-party protocol where T of them could be malicious, and the goal is to agree on a single bit. So pictorially, this is what it will look like. We have n parties. Each of them has a bit. And then they input this bit to a binary agreement protocol, and they receive a single bit output from the binary agreement protocol. And we want this BA box to satisfy some properties. First is the agreement property, which says any two honest parties output the same bit. And it should also satisfy some validity property, which means that if all honest parties input the same bit, then they should output the same bit as well. And we also want that the protocol terminates. So in this paper, we look at a slightly different variant of this consensus problem, which is also known as common subset or the interactive consistency problem. Here, it's again an n-party protocol with up to T failures, but now the goal is to agree on a subset of inputs. So we have parties, and each party has an input. Here, I'll use MI to denote the input of that party, and they provide this input to a common subset protocol, and the end goal is to output a subset of messages, capital M, M1 for party 1, M2 for party 2, and so on and so forth. Now we want, and these messages belong to some of the parties that they provided input to. And we, again, want some nice properties. First is the agreement property, which says any two honest parties output the same subset of messages. And also we want validity property, which says the set they output contains at least n-2t honest inputs. And also we want the protocol to terminate. This common subset primitive has many applications. So we're in the blockchain session, so the obvious application is the blockchain. But we can also use this for secure multi-party computation. We can also use this for distributed key generation protocol. We want to solve this common subset problem in the asynchronous networks. Let's define what it is. So it's a network model where message delays could be arbitrarily long. But the guarantee is you want that the messages must eventually arrive. So pictorially, this is what it will look like. Let's say we have two honest parties. If a party sends a message to the other party, the message can be delayed arbitrarily long by the adversary, but the message must eventually have to arrive. And this is very good to model internet-like network where you don't really have control over the message delays. Okay, so we want to solve this asynchronous subset problem, common subset problem in asynchrony. And this is what it looks like. You can imagine we want to solve it for nodes that are running over the internet, do not have dedicated connection. But here is one problem, that we know that deterministic asynchronous consensus is impossible. And this is a very classic result by FLP. So what do we do? But we have a savior here. The impossibility result says the protocol, it is impossible only if the protocols are deterministic. So we'll rely on randomness. So we know how to construct ACS protocol, asynchronous common subset protocol, which are randomized. So we have the ACS primitive as is. If we feed in some source of randomness, it could be shared randomness, it could be local randomness, we can solve this ACS problem. Okay? So now the problem boils down to how do we build a common coin protocol in asynchrony? And if you have worked in this area, you'll know that to build common coin, we rely on ACS. So to repeat, if we want to build a common coin in asynchrony, we need to use ACS. But here we have seen that if we want to solve ACS, we need the common coin. So we get this circular dependency. And this is why this problem is harder to solve. But fortunately, we know how to get past these impossibility results, and there are many, many results. I'll highlight some of the ones. So these are state-of-the-art, according to me, in the asynchronous common subset protocol that doesn't rely on prior setups. But these get really nice communication cost. If I can point, okay. They get really nice communication cost of kappa and cube, and they also have very, very good round complexity. But if you look at what kind of assumptions they use, these are public key crypto assumptions. And we don't want them because they are not secure in the presence of quantum computers. But okay, let's not use public key crypto. Let's try to do information theoretic asynchronous common subset. And indeed, there are works. The state-of-the-art work does achieve an information theoretic asynchronous common subset protocol, but it requires 10 to the 5 communication cost. And also, it can only tolerate n over 4 malicious parties. So it's not optimal fault tolerant. So in this paper, we asked, can we design a post-quantum secure ACS protocol without any setup? And the answer is yes. And this is what we get. We get a protocol which just relies on hash functions, and it achieves communication cost, which is similar to prior ACS protocol with public key crypto, and also get a good round complexity. And the natural question is this protocol efficient? And the answer is also yes. Okay, so we'll now look into some of the constructions. Before that, let's look at some of the background. So one primitive that we'll use is this threshold secret sharing. You might have seen this in some of the talks before. So this is again parameterized by N and T, where we have a protocol. It's a mechanism to share a secret among N parties. So we have a secret. We want to divide the secret into N pieces such that any subset of T plus 1 shares lets you recover the secret, but a subset of T or less doesn't reveal anything about the secret. And this is the classic Shamir secret sharing scheme, where we embed the secret as the constant term of a low-degree polynomial, and each share is one evaluation point on the polynomial. What we need is something called verifiable secret sharing, which you can think of is a protocol among n parties to share a secret with the additional properties that parties who receive shares can locally verify that they are receiving valid shares. I won't go into the details of how to construct this, but these primitives exist even in asynchronous setting. Okay, another primitive we need is called reliable broadcast. This is a very old primitive. So here the goal is we have a broadcaster that wants to broadcast a message M to all the parties. And if we do simple protocols where the broadcaster simply sends the message to everybody, then it won't work, because if the broadcaster is malicious, then it can send different messages to different parties, and it may not send some messages to parties as well. So we want to do something special, and we already know how to do it even for short messages, even for long messages. So this is also we'll use as a prior work. Okay. The third primitive we need is something called index gather. So this is an asynchronous consensus protocol, but with a weak agreement property. And we weaken the agreement property to be able to bypass this FLP impossibility result. But to define this property, I need to define this notion of party validation, which says parties can validate each other based on some local action. It just means if I'm a participating party in the protocol, I can see whether what other actions other parties are doing, and I'll have a local state of whether I think some party is valid according to some function. So once I define this party validation notion, I can define the index gather protocol. So this is, again, it's a protocol among n parties, and each party has an input, which is a set VI. And VI is the set of parties party I has locally validated. So this is just a purely local notion of validation. And then they provide this input to an index gather protocol and receive an output from the index gather protocol. These XIs are subset of parties. So each party receives a set XI. So what properties do we want from the index gather protocol? First is we want that the protocol terminates. And the second property we want that each party outputs at least n minus t, or the second property we want is the validity property. It says the output only contains valid parties for some notion of validity that we define in the paper. And the third and crucial property we need is the binding core property. It says when the first honest party outputs from the index gather protocol, there exists a core set that you can define as a function of the intermediate state of all the parties, such that every party will eventually output a superset of this core set. Okay? So I'll probably just give you 10 seconds to look at this again. It just says when the first party outputs, we can define a core set X, which is large enough, and everybody will output a superset of this core set. And this is not a new primitive. If you look hard, it dates back to Canity-Revin 93. So this is a very old primitive. Okay? So once we have all the backgrounds, we can now ready to talk about how to construct an ACS protocol. Okay, so the ACS, there are many flavors to do a asynchronous common subset. I'll look at one particular flavor which uses weak leader election. So this protocol proceeds in iterations, and each iteration has two phases. The first is the random weak leader election phase, which will output a party index I, and then we use this party index I to run an agreement protocol. And then we repeat. Well, the random leader election protocol is weak in a sense that parties might disagree with who this leader is with constant probability. Recall, we cannot solve consensus yet because we haven't used randomization yet because of the FLP impossibility. Okay, so this is a weak kind of agreement property. But the property we get is that when parties agree on who the leader is, and if the leader is honest, then the protocol can terminate. So again, if you can see that we'll do it again and again until parties agree on who the honest leader is, and whenever they do, they will terminate. So this is how a class of ACS protocol works. Okay, and in this talk, I'll just focus on the random weak leader election primitive. Okay, let's design a weak leader election protocol. So this is a simple protocol, I'll say. So we can assign each party a random rank, and we can pick the party with the highest rank as the leader. This is what it will look like pictorially. We have parties. We can assign ranks to each party. Let's say Ri is the rank of the party. We assign them ranks uniformly at random. And pick the party with highest rank. Let's say R4 is as our leader. And this is easy with an external common coin. If we have a shared coin, then we can easily pick one leader. But we don't want to rely on external common coin because they already rely on ACS. We have this whole circularity, so we want to do something different. Okay, so let's look at one way to construct a weak leader election protocol without external common coin. And from now, the talk will be a bit more technical for about 5-10 minutes. Okay, so we have parties. So each party locally samples a random secret and will share the secret with everybody using a verifiable secret sharing scheme. Recall, it's a scheme to share a secret among n parties so that T+1 parties can recover the secret. So everybody will do this in parallel. So each party is sampling a random secret and sharing it with everybody. And then each party locally waits to see who all did the verifiable secret sharing correctly. So party 1 will locally wait to see and then collect a subset of parties which it thinks that did the VSS phase correctly. And let's call this set to be P1. Party 2 will also locally collect a set. Let's call this P2. Each party will do that. Note that parties might disagree on what the set is because, again, we are in asynchrony. We haven't run any agreement protocol yet. Okay. Now then parties will put this, the set that they have collected through a reliable broadcast protocol, which is just a protocol to send a message to everybody, the same message to everybody. So everybody will do this in parallel. Then each party waits to locally identify a set of indices which it thinks that did the reliable broadcast correctly. So let's call this set X1. Party 1 will think, oh, party 1, 2, and 3 did the reliable broadcast correctly. Similarly, party 2 will also collect a set, party 3, so on and so forth. Okay? Now each party has a local set of what they think are the parties did the reliable broadcast correctly. Now once we have the set, they input the set to an index gather protocol, and the index gather protocol will output a subset of parties. Let's say the index gather protocol outputs the set 1, 2, and 3, and we know since this is an index gather protocol, when the first honest party is output, there's a binding core set we can define. Let's define this set to be 1, 2, 3, such that every party will eventually output a superset of this binding core. Okay? Now then we can assign ranks of parties as simply the sum of the secret of shares shared by party P, or parties in PI. So a rank of party I is the sum of the secrets of the parties in the set PI. And the intuition is this set PI contains at least one honest party, hence and one honest contribution of uniform random values, hence the ranks will be uniformly random. And then we pick the party with the highest rank in a local view as the leader. And why it guarantees that we'll terminate in a constant probability, it's because of this exact condition, which says if the party with the highest rank in the highest global rank is part of the core set, and everybody will output a superset of the core set, hence everybody will agree on who the leader is. Okay, this is very crucial. Good. But it turns out if I exactly do this, this is insecure. So we did all this complicated protocol design just to find out that this approach is insecure. And a concrete attacker can indeed attack the system and keep it running forever by exploiting this fact. It will ensure that the party with the highest rank is never inside the core. And I'll show how to do it, right now. Okay, let's look at the attack. So this is the protocol as is, nothing changed. So now, once an honest party outputs from the set, when honest party outputs in the gather protocol, it will reveal the shares of all these SIs to derive the rank. Now adversary can see what this SI values locally, and then it will pick a S4 for the malicious parties such that it will eventually get a higher rank than all the other parties. Then, since it controls the network, it will do the following attack that I show in this red box here. It will pick S4 such that S4 leads to highest rank, and it will do the VSS. It will stall the net communication of all the honest parties. It will rush. It will pick set P4 to be 1, 4, do the RBC, and then will control the index gather protocol such that the fourth party is included in the output of index gather protocol of every other party. Now, you can immediately say that this violates this condition that the party with the maximum rank is in the core, because the core is 1, 2, 3. Now the party with the maximum rank is 4, and it's always outside the core. And in this attack, adversary did not exploit any properties of index gather. It just manipulated the messages to do this. An adversary can do this repeatedly again and again. Okay. Good. So how this is addressed in the literature, and one way to fix this is to use public key cryptography, is to use threshold verifiable random function. So we have the protocol as is, nothing changed in this figure, but we change how we derive the ranks. So to derive the rank, we now use we define a secret key, which is the sum of the secrets shared by parties in PI. So Ki is the sum of the secrets shared by parties in PI, and then we run a public key cryptography-based threshold VRF protocol to derive the rank. But the problem is we do not know how to build a threshold VRF without using public key cryptography. And that's why this approach doesn't work. Well, this approach is secure, but it needs public key cryptography. Okay, so we'll look at our approach, what we do. Well, we define a primitive called index cover gather protocol. And this is an index gather protocol with a slightly stronger property, which we call as binding cover. So again, we have parties. Each party have input, which is VI. It's the set of parties that party I has validated. And then they input this, they provide this input to the index cover gather protocol and receives the output. Nothing changed so far. And this is an index gather protocol, so it trivially satisfies the binding core property, which says when the first honest party outputs, there exists a core set X such that everybody outputs a superset of that core set. Okay, so this is same as before. So we introduce this binding cover property, which says when the first honest party outputs, there exists a cover set Y of valid parties such that everybody outputs a subset of these parties. So the index binding core property lower bounds the output of every parties by X, and we're trying to upper bound the output of parties by a set Y. And this is, if you think of the attack, adversary could manipulate the rank because after seeing the honest parties output, it can inject one more party in the output of our remaining honest parties. Now we'll upper bound what the adversary can do by a superset Y to prevent that attack. Okay? And we give a construction of index cover gather protocol with an n-cube communication cost. Okay, so now we have this insecure weak leader election protocol. So the only change we have to do is to substitute this index gather protocol with an index cover gather protocol. That's it. And now, by the property, so we have a core set. We have a core set which will be output by this index cover gather protocol, not output, but there exists one, and then there will be a cover set which will also be part of this cover gather protocol. So now if we try to attack this protocol using the previous attack, so we have the protocol as is. Adversary can learn the secrets of parties. It can pick S4, but if the cover set is same as X, 1, 2, 3, then by the properties of index cover gather protocol, the party 4 will never be included in output of any honest party. So no matter what the adversary does for party 4, it won't influence the rank of the parties that honest parties care about. Okay, so this attack is inconsequential. Adversary can do this attack, but it won't harm the protocol. Alternatively, if the cover set is 1, 2, 3, 4, right here, so now the output can indeed have party 4, but we can ensure that if the cover set is 1, 2, 3, 4, then adversary have to fix its input S4 before any honest party outputs from the cover gather protocol. Okay, so let's just to repeat how ACS construction work. They use this iterative phase where we have a weak leader election protocol which outputs the party index I, and then we run an agreement protocol, and then we do repeat. And our main contribution is improving this random weak leader election protocol using this hash function. To summarize, we give an efficient weak leader election protocol using only hash functions. And we also have lots of concrete optimizations of the agreement phase, but those are not important for this talk. And we also give a simple hash-based weak asynchronous basis protocol, which is also described in the paper. So I'll now, okay, so I'll use maybe 5 minutes to talk about the implementation and evaluation. So we implement this protocol out of one of my previous code base on asynchronous DKG. And we use Python for networking and use BLS 12381 field operations for finite field arithmetic. And we evaluate it using up to 128 nodes. And we use 2 baselines. First is the ACS protocol from the prior DKG scheme, because that scheme has the same setup as ours. It doesn't rely on any setup, but uses public key crypto. And we also use as a baseline an ACS protocol from Fin, which rely on an idealized common coin. So the goal of our experiment is to show that our hash-based protocol, although it doesn't rely on public key cryptography, is as efficient or better than the prior public key-based crypto. And also it's not much worse than other schemes which rely on an idealized common coin. But I want to say that these experiments are evaluated on a prototype code base, and there are a lot of scopes for optimization. So let's look at some of the evaluation results. First is the bandwidth uses, which is the amount of data a party will send during this ACS protocol. And we see that we don't send too much data. That's what I just want to say. We also look at the amount of messages parties will send during the ACS protocol. And again, this is we send much fewer messages from the prior ACS protocol with public key crypto, but we send slightly higher number of messages from the idealized common coin-based protocol. Let's look at the runtime, which is the end-to-end runtime of the ACS protocol. So our runtime is better, but our runtime is worse than the Fin protocol. And I would say I would attribute this to a better implementation of Fin. So they have a much better networking library. And if we do, because our bandwidth uses, computation cost, and message counts are almost similar, so I would expect a similar runtime. But we see higher, this is because of implementation. Okay, to summarize, we present an asynchronous consensus protocol using only hash functions. It has optimal fault tolerance. It has kappa and cube communication cost, constant round complexity, and then it's a protocol with very concrete efficiency. There are some nice open problems. One is to improve the efficiency or to prove lower bounds. And the other is better implementation, and I feel that better implementation will help the community in general. If we can have a common framework where we can test all our distributed cryptography or distributed protocol, it will be very nice to have. Finally, I want to end this talk with a poem that Victor wrote about this paper. So I don't want to read the poem. You can read it yourself, and I'm ready to take questions.
We have time for a few questions. You can start lining up. Let me start with the first question. So you started the talk with this hope that this is a quantum resilient algorithm, and you used only hash functions. But these were modeled under the random oracle model. So is this the quantum variant of the random oracle model? And can you tell us a little bit about your proof?
Yeah, in the paper, we're a bit loose about proving actual quantum security. There are 2 variants of the protocol. One where we assume random oracle. There is other, we can instantiate the protocol with concrete assumption on the hash function. We don't really need random oracle, but we need assumptions which are slightly more than collision resistant hash function.
Yeah. Got it. Okay. Let's go to the questions from the audience.
Okay, thanks for the talk. I was just curious why you chose to frame your talk as about common subset instead of VABA or agreement, because the latter sounds more fundamental. I don't know.
I would say these both are pretty similar primitive. You can construct one from the other, and there was no particular choice of. If you look at the paper, we build a VABA inside, and then we build a ACS using a VABA. So if you just want VABA, you just don't read some subsections of the paper. But yes, the talk is, yeah.
Hey, thanks for the talk. I had a question on the first slide where you show the common coin construction from VSS, even before you described the attack of Party 4.
Okay.
There you showed in the last step the output of the gather protocol.
Yeah.
I think you showed in the slide that every party outputs the same set, 1, 2, 3, it was there. Right.
Yeah.
And is that a special case? Because if I remember correctly, the gather protocol, parties can output a superset of the cores. So my question is, what happens in that case? Do they disagree on the leader? And if this was reflected on your benchmarks, because then consensus can take much longer to terminate.
I think I used the example where everybody outputs 1, 2, 3 to be able to later illustrate the attack of including 4. But when the gather protocol doesn't give you this agreement property. It might happen that the output looks very similar to this where some parties are outputting 1, 2, 3 and others are outputting 1, 2, 3, 4. This is allowed. This is possible.
And with the cover protocol, do you eliminate this to some extent?
No, gather with you mean index cover gather protocol?
Yes, yes.
We do not eliminate this. It might be possible that the core set consists of n minus t parties, and the cover set consists of all n parties.
Yeah.
Now parties can output anything in between.
Yeah. But we don't have any statistical analysis how often this happens, or
no. In practice, I think it works pretty fine, but we didn't try. We didn't try to do explicit attacks. Yes. Thanks. Okay.
So 2 quick questions. One is silly. So the silly question is, I guess, presumably you still need encryption and really hybrid encryption in this, even for the VSS. But so the real question is, so a threshold VRF, okay, that's harder, but in general, hash-based signatures are not VRFs, but if you take a one-layer one without internal certificates, something like one-layer XMSS, then you do get a VRF. So the question is, can you do anything with local VRFs?
Okay, good. So to answer your first question, in the VSS, we do require private channels. And you can ask this philosophical question of how do you instantiate these private channels. You can use symmetric crypto. We can go into this philosophical discussion, but we do rely on private and authenticated channels. And to answer your second question, you are saying this XMSS gives... Okay, good. So to solve ACS, we need to have a common coin that everybody agrees on the VRF output. If you have a local VRF where each party outputs a unique value, but they output different values across parties, then we don't know how to get polynomial communication complexity protocols. There are the oldest protocols, I think, BKR, I guess, they use the local coins, but they need exponential runtimes.
Let's thanks to Rav again. Okay, the next talk and last talk of the session is called Nakamoto Consensus Under Bounded Processing Capacity. It was supposed to be given by Srivatsan Sridhar, who unfortunately couldn't make it today. So thank you, Joachim, for substituting. And Joachim Noah is going to give the talk.
Okay, fantastic. Here I am again. I wish I didn't have to. Srivatsan would love to be here and would love to give this talk. Unfortunately, he fell sick this morning, and so I'm going to give you the talk. That said, yeah, all the slides, all the work, all the slides is Srivatsan's work, so I've just added his picture here. And this important disclosure again. Welcome back. So this talk is about studying the problem of security and throughput in blockchains. This is a problem that has been studied quite a bit in the past. The standard kind of picture or the standard numbers that everybody cites are from a few years ago. These numbers that Visa in peak processes something like 25,000 transactions per second, and in contrast, popular blockchains like Bitcoin can do at most like in the tens. And somehow people have the feeling that there's quite a gap between sort of the processing capacity that each node has, both in terms of like the network connectivity, but also the ability to kind of execute transactions. So processing sort of in the wider sense, right? And the transaction throughput that we actually achieve on chain, right? So there's a gap between these, and people have been trying to sort of close that gap. increase block sizes, increase the throughput of the blockchain protocols. And other people have, called for caution and said, well, there's, some security margin here because of which the throughput is so much lower than the node's capacity. And, maybe we don't want to eat all the way into the security margin, right? And so, academics have sort of kind of entered this discussion and have in particular studied the security versus throughput trade-off as an example, for example, of Nakamoto's consensus protocol. Okay, and so it's in this line of works that also this work lies, right? So we're studying security versus throughput in Nakamoto consensus, and Nakamoto consensus is sort of the Bitcoin protocol, but besides instantiating it with proof-of-work lotteries, it has also been instantiated with proof-of-stake lotteries, such as the Ouroboros or the Snow White protocol. Okay, so we take this as an example to study these effects of security and throughput. And so if you go to the literature, sort of the main figure where people study this kind of relationship is when you plot what fraction of adversary work or adversary stake your protocol can tolerate as a function of the relative block production rate. So the rate at which blocks are produced normalized by the speed at which nodes in the network can process these blocks, right? If you look in the literature, you will find this curve, right? And this curve basically tells you that, roughly around the point where, you're producing blocks as fast as your nodes can process them, right? Your adversary resilience sort of starts tanking, and before that, you get a resilience of about 50%. Okay? So in particular, if you exceed the block production rate, if the adversary exceeds what the protocol can tolerate, then there is the well-known private attack to attack the protocol. And if the adversary is weaker than predicted by this bound, then the protocol is supposed to be secure. Okay? All this work takes place in what we call the bounded delay model. And what is that? That is, well, the key thing to analyze the security of this protocol is to sort of describe, how quickly can nodes actually process blocks that are being produced by other nodes. Okay? And in this bounded delay model, the idea is, here's my computer, and my computer receives, or any validator, any node, receives blocks, messages more generally from other computers, and the idea is any message that it receives, it can kind of process and communicate and execute and evaluate this message within a certain delay bound. Okay, for example, 1 second. Right? Now, what's the problem with this? Well, what if there's an adversary who has withheld a bunch of blocks and just suddenly dumps them all onto the network? Right? Then you would expect that, somehow now, there's a burst of work to be done. How long does it take me to kind of process that last block? Well, according to this model, still, every block, every message will be processed within 1 second. Right? That ignores, effects that we have in physical systems, which is congestion. Right? If there's bursty block production, or if the adversary dumps a bunch of blocks on the network, suddenly, then you would expect that the time it takes to process the last one of those would actually go up. Right? So you would expect a system to behave much more like a queue. Right? Real systems have bounded processing capacity, and you can only process blocks one by one. And until you get to all of these blocks, they basically kind of queue up. And so the time it takes for these blocks to actually make it through your processing system should actually go up if the load on the network increases. Right? So now if we take this model and we kind of go back to the security analysis, then what we find is actually there are ways to exploit congestion in order to sort of make it so that even weaker adversaries can attack the system. And I'll show you one example. What this means concretely, if we instantiate, for example, with the bandwidth recommended and the block production rate for systems like Bitcoin or Bitcoin Cash. If the system is parameterized fairly conservatively, you don't see much of this effect. But in particular, a system that was sort of pushing to kind of operate close to kind of the processing capacity that each node has in terms of the throughput of the blockchain, will see a considerable drop in resilience. Okay, so the key takeaway here is, when you're designing and analyzing new protocols, keep in mind the fact, that your system has bounded capacity, and you need to somehow deal with this. Right? Then this is all in the setting of proof of work Nakamoto consensus. What we also provide is a kind of a new security region, kind of a region of block production rates for which we can characterize up to what adversary fraction the protocol is secure. And then we can go to proof of stake, right? If we're in this queuing model and we're in proof of stake, then besides these 2 points that allow the adversary to drive up congestion and to attack the system, there's a third point that is important, which is that in proof of stake, you could have equivocations, equivocating blocks. So if somebody is entitled to produce a block, they can actually produce a whole bunch of copies. And so the load on your system may actually be even higher than just the blocks that the protocol would produce normally. And then you would expect that these attacks become even worse, right? And in fact, that's the case. If you want to drive down the probability of attack to 0 in an exponential fashion, then the only way you can do that is if your chain becomes slower and slower and slower. Okay. So the last result I'm going to talk a little bit about is how you can modify kind of proof of stake protocols to kind of recover this behavior of proof of work protocols that equivocations don't play a role. Okay, what you should notice is, right, in these new bounds, there is quite a gap kind of between what the attack can do and what the security result does, unlike in the previous bounded delay model, so there's a lot of room for future work there. So now I want to dive a little bit deeper into some of these aspects. First, I want to talk a little bit about the bounded capacity model, right? How do we model this system? So, in the blockchain, we have blocks consisting of a header and content. There's metadata and there are transactions. And the way we model the processing of blocks, meaning both the communication but also the execution, everything that kind of goes into this delay, is that whenever a block is produced, the header sort of gets pushed out to the network. It then, at every validator where it receives, kind of enters a queue. The validator uses some protocol-specific scheduling policy among all the headers to decide, what to execute next or what to download next. In particular, we're looking at the process the longest header chain rule first. Process the longest header chain first rule, which is used, for example, in Bitcoin and in Cardano. And then based on the header that was chosen, the validator proceeds to download that block and to execute that block. And so, that's the whole propagation process. Okay. There's a header delay, that's part of the model. There's a processing delay that basically captures kind of the capacity constraint. How long does it take for each header to kind of process the body or the content? And then the thing that's new in this is, if we want to talk about the end-to-end latency, we need to characterize the queuing delay that blocks have as they go through the queue here. Okay, and that arguably depends on the scheduling policy, and it depends on, for example, this behavior that the adversary may show of like driving up congestion, right? Withholding a bunch of blocks and then suddenly dropping a bunch of headers onto the network, kind of trying to congest our queue here so that honestly produced blocks will be delayed, and then that would undermine the security of the system. Okay, so I want to give you an example how such a congestion based, attack strategy could look like. It's just a, small toy example to give you a sense of how an adversary could use congestion in order to, try to weaken the security of the system. Right? So, for example, in Nakamoto's consensus protocol, we can say, okay, we have our genesis block, there's like an honest block here, and let's say the adversary has already, by chance, lucky for the adversary, has already produced 3 blocks, but it has withheld them, okay? It hasn't shown them to the network yet. And now an honest miner produces a new block, disseminates this header to the network. The adversary suddenly drops all these headers onto the network. Okay? Then because of the longest header chain first kind of scheduling rule, all the honest validators will now try to process the body for this adversary block here. Okay, so it'll take a while, then everybody has processed that block, right? And then they realize, oh, you know, the content of the other blocks is actually not available for download, right? I've received the header, but I'm not able to actually find the content for this. Okay, fine, so I'm gonna abandon that chain for now. I cannot proceed here. And I'm gonna stop processing now finally start processing the content of this honest block, right? But in the meantime now, in order to download this one honest block, basically the adversary had to download the honest party had to download also an adversary block, and so it basically spent 2 blocks, it had to process 2 blocks in order to advance its longest downloaded chain by 1. Okay, and in the meantime, because that takes longer than just processing 1 block, honest miners have been mining on this most recent honest block, and so there's more forking, and that undermines the security of Nakamoto consensus. Right, so this leads to delay, and yeah, we're now basically, after this, we're basically back to square one in terms of this picture, right? So if there's another honest block, then again, the adversary releases another header, and it'll again take longer to download that, for honest parties to get to downloading that block than before in the non-queuing model. So that gives you this, bound here for this congestion-based attacks, and the key takeaway again is, congestion-based attacks succeed with lower adversary power, and so you should keep those in mind when you analyze protocols. In equivocation, so in proof of stake, so previously this was all for proof of work. Now if we look at proof of stake, right, then block production is done by this proof of stake lottery, where an adversary, whenever it gets to produce a block, could actually produce a whole bunch of blocks with different transactions. And it could send all of those to the network at the same time, and then this congestion-based attack becomes even more problematic in terms of security. How do we get a security proof? Let me check time, good. So we want to still prove security, say for proof of work, for Nakamoto consensus in this queuing model. What's important there is that we characterize the queuing delay and the processing delay. In particular, the queuing delay is kind of this new quantity that wasn't there in the bounded delay model. And so we need to characterize sort of any honest message, any honestly produced block, how long does it take for it to traverse this queue until it's processed so that honest miners can mine new blocks on top. And the naive approach to doing this, which we did in an earlier work, is to give a worst case bound on this queue length. Okay, so we look at kind of overall, over the whole execution, how bad could this possibly be? It could be pretty bad. And as a result, in order to get a protocol that is secure, we need to keep reducing kind of the block production rate of the protocol. But then there is a key insight, right, which is, okay, we have this worst case bound, but most of the time the system is not in the worst case, right? There should be some sort of an average case behavior, right? The queue cannot always be full. There is only a limited supply of blocks in proof of work, and they get processed, let's say twice or 3 times, like some number times faster than they're produced. So it's not possible that the queue is like always congested, right? And so even if the adversary withholds a bunch of blocks on some side chains and it drops them on the network later, these blocks, they must be sort of old. And so we can, if we use the longest header chain first rule, then these old blocks that are from like, a long time ago, somewhere higher up in the block tree, they should not have very high priority and they should not be able to clog the network. So we do a refined proof where we basically analyze the system in this average case rather than in the worst case. And then what we obtain is security of this protocol, even at non-vanishing block rates. Okay, so that's the security result that you've seen before. This was all for proof of work, right? Except for this small detour that I did about the congestion-based attack. Now for proof of stake, this key insight that there's only a limited supply of blocks no longer holds, right? That's only the case in proof of work. In proof of stake, there could be equivocations. And the idea to sort of work with that is, is there a way to just not process these equivocations, right? Can we just like, if we know there was an equivocation, we know that whoever produced this block is malicious, so it should be somehow possible to just ignore that block, right? The problem if we do that is we need to agree that we all will ignore this block, right? If I decide to ignore it and Dionysus has maybe not seen this equivocation and decides to actually process that block, then we risk ending up in inconsistent state, right? So the idea though is, okay, if I see an equivocation, at least, since the network has like not that much delay, I can convince Dionysus that there was indeed an equivocation. And so as soon as somebody sees an equivocation, we should be able to convince each other that we should all all ignore that block, right? That's sort of the intuition. And the way we do this is as follows. So suppose there is an equivocation, right? Then there is some sort of a kind of a proof of equivocation, right? There's evidence. There's like two signatures like on two different blocks, right? By the same proposer at the same time. Then we can ignore the content of these blocks and use kind of the rest of the chain to include an equivocation proof for this equivocation. And then we make sure that this way we all agree which block's contents we will blank, and this way we will recover consistent output logs. And if we do this, we go from this picture, which basically says there's no security unless you have vanishing block production rate, back to the picture that we have seen for proof of work, which is that even with non-vanishing block production rate, you still get security. Good. That basically concludes the talk. If you want more information, check out the paper. Here's the QR code. We have some simulations there of these congestion-based attacks. We describe this POS, proof of stake Nakamoto style protocol that overcomes equivocations. And you can read the security proof under bounded capacity in the full glory. This is work that will also be presented in October at CCS. And I want to leave you with like a final note, which is something that I'm excited about with this work is, there is this kind of hidden kind of part of the iceberg when it comes to consensus protocol, security analysis, right? Most consensus protocols are analyzed in pretty simplistic network models. And if you kind of, peel away a little bit at those layers, then what you will find is that there's a whole bunch of factors that are sort of not accounted for, right? Today we talked about bounded processing capacity. Other things are network topology, network level attacks, heterogeneity among the parties that are in the network, etc. So there is still a whole bunch of things to be done. And I'm happy to take questions.
Thanks a lot for a very nice talk. So my question regards this assumption that the scheduling policy is based on the latest header. This seems really easily exploitable. I can just show you a header that I claim is very long, and you will process my blocks first. Is there another policy that would be preferred, or like have you ruled out everything else?
Good. You're asking specifically here about kind of the scheduling rule. Okay, so in the case of proof of work, what we do is, so you can't just make a claim, right, about where, about the height of your block, right? So in proof of work, we go by sort of the highest, we process the highest block first. And we're able to verify that, right? Because we see the whole header tree, so to speak. And so we just go to the longest chain in the header tree, and those are basically the blocks that we're supposed to process. In proof of work, there's a bunch of different rules. So if you look at the paper, we give the security proof assuming a handful of conditions on the scheduling policy under which we can then complete the security proof. And there's a few other sort of download rules or processing rules for which the security proof also works. In proof of work, I'm not sure they're so important. In proof of stake, there is more degrees of freedom because you have more information about when the block was produced, by who the block was produced. You could ignore equivocations, for example, or you could go by kind of the most recently produced block rather than the highest kind of block, all of those things.
All right, thank you.
What about the use of slashing in proof of stake to just punish equivocation?
Yeah, that's a very good question. That to some extent is orthogonal to this question, right? So the idea behind slashing is that if it ever comes to a safety violation, you're going to be able to slash a third of the parties, right? Here, there could be a single person signing 2 blocks, and you already don't know what to do, right? If you just take away if you just slash them, you still need to decide what you're going to do with those blocks, right? Those blocks don't go away. You still need to somehow make sure that all honest parties are treating those blocks in the same way. So slashing, gives you some deterrence against this, but it doesn't change anything about the fundamental problem.
So on your plots, you have a green region and a red region. What about the white region?
Yes, the white region is left here intentional for academics to do more work. Yes, the point here is we don't know how to close this gap. So we're not sure whether there are attacks that exploit congestion that are better than the one that I've shown you, or whether there is an analysis that is better than the one you can find in the paper that basically improves this region, or plausibly maybe both. But yeah, the analysis we have and the attacks we have are not tight, and so it's not so clear what happens in between here.
Let's thank the speaker again. And this concludes Consensus 2. Let's have a 30-minute break and resume for the next session.
Afternoon, everyone. So now we're going to begin our final session of the Science of Blockchain Conference 2024, which is a session on DeFi. So Ethan Bookman is going to be your first speaker for this session. Ethan is the co-founder of Cosmos. He's the CEO of Informal Systems, and he is the CEO of Cycles, which is the protocol he'll be talking about today.
Hi, everyone. Should I use the podium or should I stroll across the floor? I think I'll double fist and stroll. All right, let's kick it off. So I'm Ethan. Thanks, Dan. I'm excited to be here in sunny Palo Alto with all of you today. Excited to be back at SBC talking about something a little bit different, the Cycles protocol. This is an application we're building to address what we consider key design challenges in monetary and financial system design. This is work with our team at Cycles at Informal. We're building a team there. We've written a paper. I have some co-conspirators, Paulo, Shoaib, Andrew Miller, and Tomasz. Andrew is in the audience here when he's not out TEE pilling random New Yorkers. But yeah, let's get into it. So I figured I'd start with some motivation and a motivational quote for all of you. None of your tokens are money, and you all have brain damage. If you don't follow me on Twitter, I don't recommend it. You'll just get more of this. But I did give a talk with this title at the Nebular Summit. You can check that out. I was recently advised that this audience in particular won't appreciate having their intelligence insulted the same way as certain other audiences I'm used to, so I won't berate you any further with that. So let's talk about Bitcoin, a peer-to-peer electronic cash system. I think many of us are here because of our excitement, initial excitement around Bitcoin and around the idea that, hey, this might be a quite profound monetary revolution afoot. Of course, it hasn't quite precipitated the level of revolution I think we were all hoping for. It has had some meaningful impact. You know, it does have a seat at the world stage in a sense, but there's still something missing. And I think a lot of that has to do with the overemphasis in Bitcoin and in the crypto ecosystem on the sort of store of value function of money and on the asset side of the balance sheet, right? We all behave as if, oh, if only we could build counterparty-free, permissionless assets, then we could take on the banking system. But the reality is that so much of the power of banks actually comes from the liability side of the balance sheet. And so an electronic cash system is not sufficient. What we need is an electronic clearing system, because clearing will actually address the debt side, the liability side of the balance sheet, and actually provides us a superset of a cash system. So as we'll see, you can embed a cash system within a clearing system. I should note, I am from Toronto, and I'm greatly ashamed that this is the most popular thing our city has to produce. But he makes for good memes. So I want to tell you just a brief story. For centuries, you know, talking about debts and liabilities and clearing, for centuries, banks have formed closed clearing clubs to pay off huge amounts of debt with little or even no money, right? And this is a massive source of their power. They build up all these liabilities between themselves, and then they get together and net them out. But you and I aren't privy to these clubs, unless there's any bankers in the audience. Are there any bankers in the audience today? No? I'm sorry to hear that. Or go us. But you know, even if there were bankers in the audience, even they wouldn't be able to participate in these clubs as individuals, only as institutions, right? So what we have here is a visualization of us poor, depraved souls, you know, begging, desperate to get inside these clearing clubs to access the enormous power of clearing and of issuance. And it really is a power, because the rest of us are forced to settle our debts in cold, hard cash. Until now, of course, with Cycles, anyone can clear their debts in a private, secure, and accessible way using any type of currency or credit that works for them, right? So Cycles is really about enabling, you know, new kinds of economic relations to form, for people to be able to issue currencies in a meaningful way and use them to clear their debts. And this is all made possible by a very particular feature that is made possible by blockchains, right? And that's atomic multilateral settlement. I think this is really the killer feature of blockchains. Atomic multilateral settlement allows many people to participate in a single settlement operation in an atomic way. And this is what's required for us to do this kind of clearing and to build an open clearing protocol that anyone can use. And of course, we want to take it further and make it private, and we'll talk about that as well. So let's briefly talk about payment systems. Payment systems are really the foundation of finance. So much of finance is built on top of payments. It's a extrapolation of what's required for payments. I like to say that money is where the payments are. And I want to start with a brief critique of existing payment systems. And not to say that we're going to replace existing payment systems. A lot of what we're trying to do is in order to complement them. But I think critiquing where we're starting from and contrasting what we're trying to do with cycles will be helpful. So one, existing payment systems are not designed from first principles. They've just been cobbled together over the centuries, primarily in response to liquidity crises that have been plaguing us for hundreds of years. In contrast, what we're trying to do with cycles is really start from first principles, build a payment system from first principles. Two, and this is sort of related, risk management in our payment system, in our financial system, is primarily architected around central banks and lenders of last resort, which concentrate systemic risk and moral hazard at the heart of the system. And even the godfather of the lender of last resort design, Walter Bagehot, who wrote the book on this stuff, does not think this is a good system. But nobody will tell you that, except for me, apparently, or if you actually go and read the book, which I'll encourage you to do. It's called Lombard Street. So with cycles, we're actually starting from a position of how do we reduce risk in the payment system by thinking about the network structure that already exists, the network structure of debts, and take a more preemptive approach rather than the reactive approach to managing liquidity and mitigating crises. Third, there's a profound overemphasis on transfer and exchange of assets, and we're guilty of this in crypto as well. But the reason transfer and exchange of assets is important is because of the underlying debt that you're ultimately trying to discharge. If you're not engaging in debts, in obligations, you're not participating in the real world, frankly, right? Everything we do involves obligations to each other. So much of life is paying rents and paying wages and paying bills and paying invoices and trade credit, all this stuff, right? And we don't represent any of it in the structure of our payment systems. It's over-focused on the asset side. And again, we're missing out because there's structure in the debt graph that we can take advantage of, as we'll see. And of course, that's part of the design of cycles, is to actually surface that graph of debts and do something about it. Fourth, so much of our financial architecture is built around financial intermediaries and novation. Novation means changing the counterparties in a contract. Things like securitization and factoring, where you're mutating risk, right? What we're trying to do with cycles is instead use novation as a last resort. Try to do as much as possible with the existing structure of the graph of liabilities out there in the world, respect that graph, so to speak, before we try to do things like securitize debt or transmutate risk in these weird, complex ways that involve intermediaries and so on, which should resonate with a lot of blockchain people. Fifth, so much of the system is designed around market-making dealer intermediaries that are short volatility, that have to get bailed out by central banks, and that we're obsessed with this idea of providing liquidity into the market, right? I gave a whole talk on this at the Modular Summit called Defund the Dealers. I encourage you to check that out. In contrast, what we're trying to do with cycles is focus on the idea of liquidity saving rather than liquidity provisioning, taking advantage, again, of structure within the graph of debts to save liquidity rather than depend on these dealer intermediaries. And again, the idea is that we can actually defund the dealers to a significant extent. There's a wonderful book on this topic called The End of Finance that really contrasts these different paradigms of liquidity providing and liquidity saving. Finally, the problem of issuance, right? So much of the world's money is issued by commercial banks. A lot of us are over-focused on the money issued by central banks. I think that's much less relevant. In the cryptocurrency community, we're interested in issuing tokens to miners and validators, liquidity providers, and so on. But there's a lot more to really explore here. And as Hyman Minsky, a great economist, said, it's easy to issue money, it's hard to get it accepted. And with cycles, we're really trying to capture the nature of that problem by formalizing what it means to accept a currency, to enable us to design new kinds of currencies and issuance mechanisms that empower people and communities in ways that currently only banks are empowered to issue money. So this was a lot. I hope you don't feel too overloaded. If you need just a single takeaway, respect the graph. Okay, there's a graph of liabilities out there in the world, and that's the thing that we want to respect and honor and take advantage of. And just to zoom out, I mean, this idea that money is where the payments are, we're trying to set out conceptual concepts, not just for us and what we're building, but for everyone to really, ground how we think about building payments and finance. And, the simplest way I can think about money is that it's for denominating and discharging debt, right? It's for making payments. And you have the functions of money that can be understood very simply in this conception, right? The unit of account is for denominating debt. The medium of exchange is for discharging debt here and now. The store of value is for discharging debt elsewhere or later. And so much of our focus in crypto has been on the store of value function, a little bit on the medium of exchange function, but really only with stablecoins, right? But there's a more general conception that we can have to apply these functions as we build systems that serve the different functions of money, and that's sort of what we're going to be talking about. So, I like to ask myself this question. Armed with a unit of account, we can denominate unlimited amounts of debt. Right? I can say you owe me $1 million, and if you accept it, now there's another $1 million of debt in the world. But how do we actually know that we can discharge all that debt, that there's enough exchange media in the world to actually discharge all the debt that's been created, right? And this is the thing that provokes the anxiety among people that want to say that, you know, fractional reserve is a Ponzi scheme, and maybe it is because everyone's so anxious, there's so much debt being created, how do we know it's all going to be discharged? And often we find out it can't, and it seizes up in these liquidity crises, right? So this is the problem we want to really tune to, and this is really what liquidity is, right? Liquidity is the ability to discharge your debts when they're due, right? You can be insolvent for a long time, but liquidity kills you quick, right? And so this really motivates the question for us, you know, thinking about this problem of liquidity and making sure we can discharge debts, it motivates this larger goal. How can we build a system that can clear the most debt for the most people with the least money? And use this as a foundation for building payment systems and building up to the rest of a financial system from that. And we think we can do that with cycles. So let's get into the design of a payments and financial system that respects the graph. Do I have a pointer? No, just a mouse. That's fun. Okay, so we're going to start with basic primitives, right? The goal is to start from first principles and build our way up. And like any great modern crypto system today, we start with a system of intents, and it's quite simple. We have two input intents that we call obligations and acceptances, and one output that we call a set-off notice, and we'll describe those all in more detail. Let's start with obligations, right? This is just a refresher. We're all used to this image on the left. This is what happens every time you transfer assets, right? Alice is transferring $20 to Bob. She's making a payment of $20 to Bob. There's no liabilities involved, right? But what's missing from that picture is the underlying debt that Alice had to Bob that she's trying to discharge by transferring those assets. So that's represented on the right. Alice actually has a debt to Bob. That's the obligation. She owes Bob $20. Bob has a receivable, an asset. He's owed money from Alice. And we have to combine these two images to get the whole picture. Alice is transferring $20 in order to discharge the debt that she already had, right? And the reason this is important is because these obligations are really a missing primitive in our larger system design. In blockchains, we almost, universally fail to represent them on chain, but they form this, very robust graph. There's so much structure in the network of obligations out there that we can take advantage of, right? As we'll see, there's a huge amount of liquidity that actually resides within the graph itself, and that's what we want to harness, right? So I'm once again asking you to respect the graph. So let's talk about set-off notices. So, if you have this situation, which actually occurs more often than you might think, where Alice owes Bob, Bob owes Carol, and Carol owes Alice, right? So you have a cycle of obligations. What you can do is actually clear the smallest amount from all of them. In this case, that's 20. And we call that clearing a set-off notice, right? So when you solve over this cycle, you produce a set-off notice of 20 that you can issue to all the members in the cycle so that they can all reduce their debt, reduce their obligations by that amount. So you go from before to after, you've reduced a bunch of debt. So the set-off notice is the sort of operator, the thing that operates on the graph of intents to actually change them or reduce them, right? Now, I mentioned there's another kind of intent called acceptances, and we really wanted to capture this idea of being willing to accept a particular currency. So let's get into that. So here, the best way to understand this is with a very simple example. Alice owes Bob $20, and Alice has $20 in the bank. So we're going to use bank for now, just because it's simple, right? And it's well understood that when you have money in the bank, that's actually the bank's obligation to you, right? That's your deposit in the bank is the bank's liability. It's on the liability side of the bank's balance sheet. So the bank owes Alice $20. That's what it means for her to have $20, and she owes Bob, and we just kind of take for granted that everyone accepts bank money, right? That you can, when you transfer someone bank money, it's legitimate and they accept it. But we're going to formally represent that as what we call an acceptance, right? And so we represent our obligations as solid arrows. We represent our acceptances as dotted arrows. And when we apply our set-off notices, there's a very simple kind of mechanism at work here. Obligations are reduced or eliminated, and acceptances become obligations going the other way. So what is an obligation is a debt from the past. What is an acceptance? It's a willingness to have a debt in the future, right? So if Bob has an acceptance to the bank, Bob is willing to be owed by the bank. That's what that means. He's willing to have an obligation back from the bank, and so that's what we get. But we can actually generalize this not just to banks, but to any asset, right? So here I've just replaced the bank with Bitcoin. And we're so used to thinking about Bitcoin as a counterparty-free asset. How dare you get up here and introduce liabilities into our, esteemed liability-free Bitcoin blockchain? But it actually helps us to represent any positive balance, any asset that you hold, as a liability from the asset's issuer. When you have a Bitcoin, the Bitcoin blockchain has a God-given duty to you to let you use the Bitcoin protocol, right? You can transfer those Bitcoin following the Bitcoin protocol. That is the Bitcoin protocol's obligation to you as a Bitcoin holder, right? So any asset you hold can actually be represented as an obligation from that asset's issuer. And this is important and interesting because it means the liquidity sources can be included as nodes in the graph, right? So when we're thinking about this graph of obligations, it's not just between individuals. Also, the liquidity sources are part of the graph. The Bitcoin blockchain that issues Bitcoin, the asset, is a node within our larger graph that we can find cycles within, right? And if you look closely, what you're seeing is that every payment is a cycle, right? This is just Alice paying Bob. You would think, oh, there's no cycle there. It's just a unilateral action. But if you think about the obligation from the liquidity source and the acceptance to the liquidity source, there is always a cycle when you make a payment. So every payment is a cycle, no matter what, every time, right? And once you start thinking about that, you can generalize much further and things start to get very interesting. Now, I introduced acceptances as, Bob being willing to accept money in the bank, Bob being willing to accept Bitcoin, right? That's what this is. But what about the bank being willing to be owed by Alice? This is effectively a credit line. We can represent a credit line as an acceptance, right? So the only thing that's changed here from this picture is that instead of Alice having a positive balance in the bank, she has a credit line from the bank that she can draw on, right? So the bank has an acceptance to Alice. The bank is willing to be owed by Alice. The bank has extended a credit line to Alice. Alice can now draw on that credit line to pay Bob, and we follow our simple mechanics. The acceptance becomes an obligation going the other way. So now Alice owes the bank, and Bob has money in the bank, so the bank owes Bob, right? So we can use acceptances to represent arbitrary kinds of lending protocols, essentially here. And we can now remove the bank altogether and introduce Carol, right? So let's replace the bank with Carol. Now we have Alice owes Bob, owes Carol. And here, Carol is actually willing to extend an acceptance to Alice. Carol is willing to extend what we call a peer-to-peer loan to Alice. So this creates a cycle. So now we can apply our set-off notices and follow the same rules. And now actually no money had to move in this equation. We cleared a bunch of debt, and now Alice owes Carol, right? And this kind of situation can exist all across the economy. There are places where all kinds of debt might be able to be cleared if only we could surface the graph structure of the liabilities in the world and allow people to express their willingness to be owed by each other, right? The fact that Carol might be willing to be owed by Alice it's not otherwise possible to discover that or to take advantage of that. But those kinds of credit relationships might exist all across the economy, can advance the clearing of debts, which can reduce working capital costs, reduce risk, save on late payments, all these kind of beneficial impacts, right? So, system of intents, obligation, debts from the past, acceptances, debts in the future, set-off notice, how much an obligation or acceptance is going to be discharged by. We put this all together, we can get very complex graphs, like this one I just threw together here with obligations and acceptances. There may be liquidity sources in the graph, but in the world of cycles, there's no difference between a user and a liquidity source, right? The only way you really might figure out that it's a liquidity source is if there's a lot of acceptances to it. That's kind of what it means to be a bank or to be a Bitcoin or to be a medium of exchange, that a lot of people accept it, right? But we want to surface that graphically, right? We want to start from the graph theory to develop our sense of finance and money and economics. And once you have this graph, then you enter this problem of doing graph solving, right? You need to find some flow over the graph. You need to find all the cycles in the graph. And there are various different ways to do that. And with cycles, what we want to enable is a network or a marketplace of solvers to emerge that run different graph flow algorithms that users can opt into. And there's different kinds of optimizations that can happen here. There's the sort of standard min cost max flow, but even in min cost max flow, where you find a maximum flow through the graph, you subtract that, and you're left with the cyclic structure, so you're left with all the cycles. The solution is not unique. So there's actually many potential solutions that all give you the same amount of debt cleared overall, but they might have different people benefiting, right? And so then you can start thinking about, well, how do you select between who gets to benefit? There's all kinds of political, economic, conditions that you can apply here. You can change the optimization function. Maybe you want to make it so that the maximum number of users will benefit from the debt cleared, or you want to define some form of social impact. Maybe you want to benefit certain kinds of actors like nonprofits or well-connected or people that are using the network more, or universities, whatever it might be. Maybe you want to set the optimization so that you minimize the number of new obligations that are created. There's a lot of potential here, right? And again, because we can integrate liquidity sources directly in the graph so that you don't even know, all kinds of debt can be cleared by the use of different kinds of liquidity sources. And the graph, the solvers can just find the cycles without really having to worry about what's a liquidity source and what's not. So we get this sort of neutral solving layer that we can then apply a lot more business logic on top. To give you a sort of more concrete example of multiple liquidity sources being used to clear debt, here we have USDC, we have Atom, we have A owes B owes C, we have D owes B owes E, right? So 2 chains of obligations. Now A wants to pay with USDC, and C wants to accept USDC. D wants to pay with Atom, and E wants to accept Atom. And our friend B here is a Bitcoin maximalist. He doesn't want to touch any of these shit coins. You know, he's only willing to interact with Bitcoin. But he benefits from both USDC and Atom being used in the network because B gets all of the debt cleared, A's USDC gets transferred to C, D's Atom gets transferred to E, and B benefits, right? So B is actually benefiting from other people using Atom and USDC without him having anything to do with them at all, which is potentially very, very impactful. We can take this a step further. Now we no longer have, you know, just to see the difference, we no longer have closed loops within each liquidity source. Now we have to actually solve a single cycle across multiple liquidity source, right? A owes B owes E, A wants to pay in USDC, E wants to accept Atom. That's not going to work. But because we have another flow, we can go back the other way. Again, A's USDC can be transferred to C, even though A doesn't actually have an obligation chain to C, right? Because that we can treat the liquidity sources as nodes within the graph that we solve over, we can clear a lot more debt for more people with less money, right? And so when we put this all together, we get, you know, these very complex graphs with many different liquidity sources. And the key point here is that a small number of people being willing to use a particular currency or a cryptocurrency can actually benefit a much larger number of people who don't want anything to do with that currency, right? So stick that in your no-coiner pipe and smoke it, because we can actually, you know, this is a profound way for us to actually get cryptocurrency usage in the real world just by having people start to use, you know, upload their obligations and apply set-off notices that come from other people using these currencies. So that's potentially very impactful. To show this graphically, we put together this graph. This is based on anonymized Italian data from over 1 million invoices and around 700,000 companies. What we're showing here in blue, this blue line, is the, I wish I had a clicker, the blue line is the total amount of debt cleared in the network as a function of the liquidity injected. So liquidity is given as a fraction of the total debt. So you can see, for instance, when 20% of the total debt is injected as liquidity, right? Liquidity equal to 20% of the total debt is injected. Normally you'd be like, oh, if there's $1 million of debt, you're gonna need $1 million of cash to settle all that debt, right? The point is you need much less. And so with only, you know, $2 million, or sorry, $200,000, 20% of the total debt injected as liquidity, you can clear, see the blue line, up to 50% of the debt. Right? So there's a multiplier effect on the liquidity that more debt can be cleared with less money. And of course, at some point, it saturates, right? With only 70% of the debt as liquidity, you can clear all of it. The red line is actually showing the average debt cleared per firm, right? Rather than the total. And you see this interesting behavior, right? Where it sort of peaks, and then what happens, those flat areas are where singular large firms are getting a lot of their debt cleared. So the total debt in the network being cleared is still going up, but the average debt is not going up because it's only benefiting one firm for a while until all those big firms get cleared out, and then it starts shooting up again, right? So there's very interesting dynamics happening when you respect the graph, when you tune to the graph structure and you talk about the liquidity and how you're solving in it, and how it can benefit different people, and you can define all kinds of interesting optimization functions over it. Okay. That's our design. Let's move into talking about the protocol, right? And our goal here is to build private, atomic, multilateral settlement in an extensible credit environment. Using the design we just laid out, so just to restate, our problem statement, we want atomic execution of set-off notices and balance changes, right? So we need people's balances to be able to change, people to get set-off notices that apply atomically across many different people at once. This is a new, new kind of operation that people maybe aren't used to. We want privacy for both the obligation graph and the amounts, right? And we want an extensible credit environment so that many different kinds of liquidity sources can be integrated here, as well as lending protocols, both built directly on the platform and external lending protocols as well. And so just to briefly go over the architecture, it uses a TEE sidecar. Essentially, we're working with Andrew, so of course there's a TEE involved somewhere. And we're building a framework called Quartz, which is designed to allow, to enable TEE sidecars for arbitrary, smart contract environments, starting with CosmWasm. But the essential idea is that the user encrypts their intents to the enclave pulls down the intents, decrypts them, runs a solver, re-encrypts them, and then re-encrypts the results, and then submits everything back to the chain. And then the chain will, verify a zero-knowledge proof that was produced in the solver. It will apply any state updates, and it'll commit any other encrypted results that can then be fetched by the user, right? So if I was trying to fit in, I might tell you that Cycles is an intent-centric ZK rollup, but I'm not, so I won't. So let's talk about TEs and zero-knowledge proofs. And we're using these two things together. You know, the problem with zero-knowledge proofs and privacy is that there's no privacy from the prover, right? It gives you privacy from the verifier, but the prover, we're doing this global operation. We're running a graph flow algorithm over a large amount of data from many different users, all coming together. We don't want anyone to have access to all of that. One day, hopefully, we'll be able to use multi-party computation for this sort of stuff. But in the meantime, to do it practically and efficiently, we run it all in a trusted execution enclave. And then in order not to trust the enclave too much, we produce a zero-knowledge proof, right? So, you know, one way we could think about this is that we're running this, quadratic complexity, say, algorithm, graph flow algorithm, in the enclave, and then we produce a zero-knowledge proof of a lower complexity solution that is going to be verified on-chain, right? So what does the proof have to do? Just to give you a bit of a flavor for it, the proof needs to prove, in order to not trust the TEE for anything except for privacy, it needs to prove that the intents were decrypted correctly, that all parties ascertained, both parties ascertained each intent, right, so, i.e. signed or accepted, that the flow result is a subset of the inputs, that it's actually part of the input set, that the flow is balanced so that it's actually valid, so no one's going to like accidentally get money out of nowhere without it being balanced by someone else, and that the results are correctly encrypted, right? And so we put that all together into a zero-knowledge proof that can then be verified on-chain so that we can reduce our trust in the enclave. And then, of course, because we want to produce a proof over a huge graph potentially, there's some interesting optimizations we can do to make this scale. We can do proactive client proving, so we can get the clients to actually generate part of the zero-knowledge proof that they have the data for, that we'll be able to use more efficiently in the enclave. And we can also decompose the large proof and parallelize and put it all back together via Merkleization. So there's some nice techniques that we're working on there to make this more scalable. So ultimately, the architecture, to summarize, all the user intents are encrypted, an enclave for private graph flow, the zero-knowledge proofs for integrity, and so we don't have to trust the enclave for correctness. The set-off notices are encrypted. Those are just applied by users or their accountants to their balance sheet. The balance changes initially are transparent because we're talking about, essentially a transparent ledger, but they're batched, right? So all you see is just like a batch of balance changes that happen together atomically. Future work, we'd like to incorporate a proper shielded pool. And then, of course, we want to be able to query the state of the system using the TEE and securing that using an ORAM library. And so, a lot of people, you hear TE, you get worried about TE vulnerabilities and, how do you mitigate side channel attacks and all this. We have a relatively straightforward way to do that actually dramatically reduces the surface area of the enclave, and that's to stick a light client inside of it, right? And so that every interaction with the enclave has to do a round trip with the blockchain, which dramatically reduces your ability to grind or replay or execute code within the enclave and reduces the side channel attack. So I gave a talk on this kind of stuff with Andrew's help called How to Win Friends and TEE Fluence People. That was at Modular and also at the Flashbots MEV Day in Brussels. The problem I've been having the last couple months, like investigating TEs and SGX, is that like every time I talk to Andrew, I get more confidence that like things are going to be okay. And then every time I talk to Sylvain Bellemare, if he's in the audience, I get like more afraid that it's all for naught and it's all going to be broken. And so I just keep going back and forth. I think that's a very healthy dynamic for me, at least. The next, moving on from the privacy, the next kind of interesting thing about cycles and the sort of final component of the problem statement is this extensibility, right? And there's actually quite a bit that could be said about this, but the core idea here is that, like I've been trying to emphasize, every account, whether a user or a smart contract, is actually a node in the graph and is also a balance sheet, right? We sort of want to take this first principles approach to accounting and building a payment system. Every user is a balance sheet, every node is a node, and every node is a balance sheet. But every node is also a liquidity source, and every liquidity source is a node in the graph, right? And that basically means that by default, just by the nature of acceptances, every account is actually a lending protocol, which opens up all kinds of interesting possibilities for lending protocol design, stablecoin design, building financial systems on this kind of architecture using these basic primitives of obligations and acceptances to represent trust in the structure of the graph. And when you're operating in a clearing environment where the goal, where you're running these solvers that clear a large amount of debt for a large amount of people, you have like a, by default, risk-reduced environment for building lending protocols, right? And so that's the sort of thing I was talking about initially with how do we approach risk from a preemptive perspective rather than reactive with with sort of a lender of last resort, what is the first resort we can take? Well, it's to build clearing in from the beginning so that we're always focused on balance sheet reduction, on clearing as much debt as possible, and opening up new opportunities for people to participate in that clearing process, right? So that creates all kinds of potential for new sorts of applications, right? When every account is a lending protocol, there's quite a bit you can do with that. You get auto repayment of loans, you can have new kinds of database lending protocols and stable coins, you can have a private funding for businesses, peer-to-peer loans with and without capital. I gave an example of that earlier. Mutual credit, Circle's UBI, other kinds of credit and issuance protocols. You can build discount ladders for peer-to-peer factoring, right? So you can provide new ways for people with excess cash to access yield within the network by allowing people to express their preferences to take discounts on their obligations for early payment, right? And you can start to build interesting new kinds of yield-bearing stablecoins and things like that, algorithmic stablecoins, what can be unburdened by what has been, so to speak. You can build exchanges, right? An exchange is just cycles without obligations, essentially, right? It's just you have assets, you have people willing to accept them, and so add obligations. You can do all kinds of more interesting things with exchange. So, there's a more extended architecture that tries to incorporate all of this. We don't have to spend too much time on that. We do want to enable existing lending protocols on other chains to plug in through sort of like inner blockchain communication and locking mechanisms, but ultimately an open protocol, open clearing protocol, payments and finance engine to clear the most debt for the most people with the least amount of money from the most preferred sources. We are hiring, we need really smart, passionate, creative business and product people to bring this amazing tech to life. So please, please come talk to us. Please come talk to me after. Thank you so much. This is Cycles. I'm Ethan, and stay connected.
We have time for about one question if someone wants to come up to the mics.
Hey, thanks for the RWC vibes at SBC. So the question is it, it's not doing token transfers anymore, so it's just intents that are being transferred among accounts? Is that the idea?
There are still token transfers because there are balance changes. I mean, effectively, just to go back to this diagram, for instance, right? What's happening here is, A has literal USDC in their account on the chain, and D has Atom in their account on the chain. And the expression of the intents is their willingness to use them for payments, and their obligations to each other, and their willingness to accept them for payments. And what ends up happening here is that A's USDC gets transferred to C. So A's USDC balance will decrease, and C's USDC balance will increase, and same thing will happen with D and E and Atom. So there is a token transfer, but it's not necessarily direct. It's happening between counterparties that might not even know about each other. A and C don't have any direct relationship. They're only connected through B. But because we're solving over the whole network, the result is that there are set-off notices and there are balance changes. And so the actual balance, and those are ZK proven so that we don't have to trust the enclave, and those balance changes are executed on chain. So A's balance will decrease, C's balance will increase, and so on. Does that make sense?
So it's like a multi-hop interledger-like protocol with TEE?
Sure, yeah. If I was trying to fit in, that's what I would say, yeah.
Okay, cool, all right.
Thanks so much, Ethan.
Thank you.
For our next talk, we have Max Resnick from Special Mechanisms Group and Consensus, who will be talking about dynamic transaction fee mechanism design.
How's it going, everyone? I think this is the microphone. Is it on? Yes? There we go. There are two ways to get a really complicated mathematical problem when you're doing economics. One of them is to take a simple problem and add a bunch of real-world features to the model to try and make your modeling of the real world as realistic as possible. And the other one is to do dynamics. So buckle up. This is a talk about a very strong assumption that mainstream transaction fee mechanism design makes. And that assumption is that users are not willing to delay their inclusion in exchange for lower fees. So in the classical models like the seminal Rough Garden 2021, Chung and Shi 2023, the users arrive and they either get into the block or they immediately disappear. But of course, anybody who works on an actual blockchain knows that this is not the case, and that users have some users are time sensitive. So for example, if a user wants to trade on a DEX, then they probably want to trade at the current prices, not the prices in 5 minutes. If they want to trade, or if they want to do some payments, like at the coffee shop, you probably don't want to be waiting 10 minutes for your transaction to confirm because your coffee is going to get cold. And if you're playing something like chess or poker or other real-time games on the blockchain, you probably don't want to wait. On the other hand, there are some that are not time sensitive. For example, if I'm just sending some money to a friend, maybe I'm willing to wait 10 minutes or 30 minutes or an hour. If I'm posting some batches, oftentimes we see these L2s are willing to delay the posting of their data onto the L1. And in particular, a big use of gas on Ethereum mainnet is contract deployment. And in that case, devs are often willing to wait a very long time to do that. So this paper is basically going to try and unify the old world of transaction fee mechanism design with this new dynamic context where users face an explicit trade-off between faster inclusion and lower fees. And we're going to do that by adapting some of the queuing techniques in Huberman, Leshno, and Molemy, which is a paper that explicitly looked at the Bitcoin fee market in a dynamic setting and modeled it. And then we're going to extend that to discrete block times, deterministic block times like we have now after the merge in Ethereum, and to 1559 as well. So our main results, I would summarize the first one as proof of stake has better UX than proof of work, and the reason for that is because block times are deterministic. And the second one is that EIP 1559 price does not converge to the right price, which is something that I think we're only just discovering now, but is an interesting discovery based on the discussions that happened at the time it went in. It actually converges to a different price if the parameters are not set correctly. And we're going to talk about how to set parameters correctly and what the suggestions for what to do about these problems that I'm about to discuss are at the end of the talk. So just to go over the model, we're going to do a queuing model. Like I said, dynamics can get complicated, but I think we tried to keep the complications to a minimum. The number of new arrivals of transactions is going to be random according to a Poisson distribution with parameter lambda. And each transaction is going to be associated with a particular type of user. So you might have users who are more time sensitive or less time sensitive. And in particular, the way we model that is that each user has a vector of two things. One of them is theta v, one of them is theta c. And theta v is their total willingness to pay for the transaction. So that might be like, I want to pay $10 to get this transaction on chain. And theta c is the delay cost per unit time. So if I am delayed 5 minutes, I get theta v minus 5 minutes times theta c. And we're going to assume that those are distributed according to a distribution f on the interval 0 to c bar. So transactions are going to be served. Oftentimes in these queuing models, we have two things. We have the arrival process and the service process. So you go to the DMV, the rate at which people arrive at the DMV is the arrival process, and the service process is the rate at which the clerk handles the activity that you're trying to do at the DMV. And so this is now moving on to the modeling of the service process. And this we're going to model as a chi-square distribution, which sounds a little bit weird to do. With 2p degrees of freedom, you can see the density there. The reason we do that is because we want to be able to model both exponential arrival from proof of work and deterministic arrival from proof of stake. And it turns out when p equals 1, you get exponential, which you can check. And if you want deterministic, you do this tricky thing where you take the limit as p and u tend to infinity with the ratio constant, and you get deterministic. And again, that's so that we can model the different arrival processes in proof of work and in proof of stake, which is particularly relevant for Ethereum, which is where I spend most of my time doing research on, which actually moved from one to the other. And so this plot is actually a plot of the transaction, of the block wait times 1 week before the merge and 1 week after the merge on Ethereum. So we can see the difference right here. One fun fact, actually, the block time went slightly down. It was about 13 seconds on average before the merge, and it's 12 seconds after the merge. So this theorem comes basically straight from revenue equivalence, and so you can see the information rent term here. But this is about the Bitcoin fee mechanism, which we're calling pay your bid here. And this theorem originally appeared in the Huberman et al. Paper that I described earlier. And basically, W star is the equilibrium wait time as a function of the equilibrium bid B star, which is, of course, a function of your wait time. And importantly, it's a function of your theta C, the cost of waiting, not the value that you have of getting the transaction on chain. And what does that tell us? Basically, what matters here is your impatience, not your total value. So you might have a contract that you think is $1 million if you deploy it, but if you're not impatient, you shouldn't be willing to pay very much. That's basically what that's saying here. And a corollary of that is that we can back out the equilibrium wait time in this pay your bid mechanism as a function of the effective load, which is a quantity that depends on the arrival process and the departure process, which you can see here. So this theorem appeared in Huberman, like I said, and you can see that in a batch service process with exponential arrivals, which is based on a priority queue, we have the equilibrium wait time here, and we have the equilibrium bid here. So this is where we extended from the results of Huberman, where we showed with deterministic using that chi-squared distribution limit trick, the equilibrium wait times and equilibrium bids when block times are deterministic like they are in proof of stake. So let's dispense with the symbols and look at the charts. Like I said earlier in the talk, I'm going to show you that proof of work has worse UX than proof of stake. And so you can see here with one transaction in the block k equals 1 and with 2 transactions in the block k equals 2, and what's nice is we were able to get actual analytic closed forms for these that we're plotting. These are not simulations, they're analytic closed forms. You can see that the equilibrium bids, which are a function of the wait time, are longer in exponential block arrival. What's some intuition we can use to think about this? Basically, what's the equilibrium wait time when you submit a transaction in Bitcoin? How long are you expecting to wait for the next block? It's always 10 minutes because that's the memoryless process, the exponential arrival process. But when you submit a transaction in Ethereum, which is a deterministic block arrival process, if you submit at 6 seconds, there's 6 seconds left to the next block. So it actually depends on when you submit, and the average is only half of the block time. And you can see that these are roughly, half of one another. So I would argue that that's most of what we're seeing here, although obviously there's a lot of complexity in the math. Okay, now I'm going to move on to our exploration of 1559, which of course is even more interesting now that Ethereum has both deterministic block times and 1559 fee market. Here, let me just go through a quick explanation of how this works. It's pretty simple. We have a gas limit, which is 30 million gas. If a block has 30 million gas, it's full. We have a gas target, which is half of that, 15 million gas today in Ethereum. And if the block is more than half full, we increase the price of gas, the base fee. If it's less than half full, we decrease the price of gas. So according to this formula. And we keep doing that, and I guess the logic is eventually this should converge to the right price, the equilibrium price, the shadow price of what people are willing to pay. And one thing we know, I should have put it up on this slide here, but there's a paper by Leonardo et al. With Barnaby Monod and Thomas Thierry on it as well, that was showing that we get the right amount. So remember I said we have a gas target. Well, if you have a target, we probably should hit it, right? So that showed that even if there was crazy stuff going on with how these guys jump up and down and the price didn't necessarily converge or was chaotic, we still got the right amount. But that still leaves the question of, did we get the right price? And the current folk intuition is like, we're using the right amount of gas, so shouldn't we get the right price? But here's a problem with that intuition. Let me show you an example. So in this example, we have 15 million gas of transactions arriving every period. Half, so 7.5 million gas of that demand is theta t equals 0, basically no, like completely patient, infinitely patient. And then the other half is extremely impatient, with a disutility of 1 for every block that they wait for inclusion. So in this model, there are 2 pricing rules that both use 15 million gas on average, which remember I told you we know we use 15 million gas with 1559, but have very different utilities and prices and revenue. So in the first one, we price the inclusion at 0. After all, that's the shadow price, right? Because we have 15 million capacity on average, and we have not enough people willing to pay for that. In the other rule, we charge 99 cents for a fast lane immediate inclusion, and $0 for inclusion if you're willing to wait 1 block. So this is basically like a monopolist price discriminating against the people who are impatient. And in this case, the impatient transactions pay 99 cents. They get included immediately, but every patient transaction pays 0 and gets included in the next block. And these are very different equilibria, but they both use 15 million gas. So, and one of them has much higher revenue than the other one, which I guess Justin Drake would be quite happy about. The thing we're going to argue is that 1559, when parameters are misspecified in particular, but even when they're correctly specified, has a problem where it can lead us to a similar outcome as that situation. There's some jumpiness in the price. It can make it so that periodically we have holidays where if you wait 1 block, you'll get a much lower price. And patient users will be willing to wait. Impatient users must pay the current high price. And we look similar to the simplified model that I just discussed. So let's see if we can see that play out. Well, this is actually 1,000 blocks, so about 3.5 hours, 3 1/3 hours of actual data from the 1559 mechanism on Ethereum. You can see the blocks that we're referencing here. You can see that this is quite spiky. And I will give full disclosure that I chose a very spiky one. But the point here is that this happens quite frequently. We're spiking from 40 gas or even lower all the way up to 65 or 70 gas in some cases on like these very short time intervals. So if you're patient, then you should just wait for one of these valleys here. But if you're impatient and you arrive when there's a spike, you have to pay the price available at the time. And so what we would argue is basically 1559 is higher revenue than the priority pay your bid mechanism because of this reason. And we're going to do an explicit model of that. We're going to consider 2 prices for simplicity. Again, we're already doing dynamics here, so we can't get too complicated. We're going to do high and low price, and transactions are going to be either high and low willingness to pay. And we're going to simulate that, and as you can see in that simulation that we did, the x and y axes here are the load of low impatience transactions and the load of high impatience transactions. And you can see with just changing the fee mechanism, nothing about the arrival process, the wait times of the low types, which are the people who are patient, are much different under 1559, much higher under 1559 than they are with a priority fee. And so we start to approach that simplified model that I showed before, where in many cases, if you're impatient, you're willing to wait, which again wasn't modeled in the kind of seminal work of Roughgarden and Xi and that whole thread of literature because it was all a static model. And here we're explicitly considering impatient and patient users, and we start to see a very key difference between 1559 and the priority fee. And I just wanted to give a shout out to Potas here, who a lot of people consider us enemies on Twitter, but I wouldn't consider us enemies. But I think I really agree with the sentiment that Ethereum is not a company. We're not a profit maximizing company. We're trying to build a system that has very low friction, as possible. And we should not price resources in order to accrue value. We should price resources in order to not be denial of service attacked. And we should have the minimum price that nodes can handle on the target hardware. And if we're using a fee mechanism that raises the price, that kind of is in direct contrast to this. If we're using a higher revenue system than the one we could use, that's certainly something that we should consider alongside the other benefits that, of course, 1559 does have, including dominant strategy, incentive compatibility, UX, and stuff like that. So let me talk about where do we go from here? What should we do about it? Here's the splurge part of the roadmap that Vitalik tweeted in December. Great name. You can see that that endgame EIP 1559 is not very filled in yet. So I'm going to attempt to add a little bit of color to that and maybe move it along a little bit and what I would suggest we do from here. So like I said earlier, like the problem of spikiness in this graph here, this is a problem that is exacerbated if the parameters delta, which is the tuning parameter of 1559, how fast it updates, is overtuned. And right now I think it's overtuned. And so here's an argument. Basically, what could we do is we could all sit down on core devs, and every hard fork we could try and tune it. And I think that's a bad equilibrium. I don't think that sounds very much like endgame to me. That sounds like adding a lever that somebody has to tune in perpetuity. So I'm going to give an argument for a auto tuning mechanism within Ethereum. So here's how that would work. Basically, if we see this situation where we have a full block, then we update the price, and now the block is less than half full, that's a sign that our updating rule was too aggressive. Because what we should really be trying to do is, given the information we have today, set a price tomorrow that is expected 15 million gas use. That's the gas target. We should expect to hit the gas target on average. And so every time we see this, we're going to decrease delta by a very tiny bit. On the other hand, if we see this kind of situation, where we have a mostly full block and then another mostly full block, that's a sign that we should have probably incremented the price a little more to be more towards the gas target. And if it's even, then delta seems pretty good. Good job, delta. We'll keep you there. And so what does that look like? Basically, this Python code would implement a 2-parameter 1559. Now we have a 1-parameter. So we'll have a delta, and we'll have a delta prime. And we will very slowly adjust delta over the course of 2 weeks to be whatever is correct. So let me go back to this, because I think this is kind of the money shot of the results that we have here, and close out. I think the takeaway I would say is that we've shown that with some good intuition here, you can see that 1559 and priority fee are very much not the same mechanism. It's not as if 1559 is the DSIC version of priority fee. They have trade-offs that we should consider, and we should consider whether we want 1559 at all, because priority fee has some advantages. But if we do want 1559, one thing we can do to bring them closer together is to tune the parameter appropriately. And we don't really want to tune the parameter on core devs every hard fork. So we should probably put something in the protocol that tunes it. And another thing I would add about that, there's these moments that we change the network substantially. So we do things like we do the London hard fork where we introduce 1559, or we do things where after the London hard fork we did proof of stake, and then that changed from deterministic to, or from exponential to deterministic arrival. So those are like big changes that we do. Recently we did 4844 in March. And these are big changes to the fee market. And so we need to adjust when we do that. And the best way to do that is auto leveling, as we suggest. So I'll be releasing an EIP soon and targeting it for the next hard fork after Pectra. And hopefully I convinced you guys that this is a step towards the EIP 1559 endgame.
We have time for a couple questions, if you line up there. First question, Max, I guess, is one way to think about the proposed change to 1559 that if you think about it as a PID controller, right now it just has a proportional term and you'd be adding a derivative term?
Yeah, exactly. And I guess I'm an economist, so I don't know what a PID controller is, but like that sounds about right. There's a question of why don't we add more derivatives, right? So my goal is to have 1559 with the right parameter to kind of mimic us setting it on core devs and do it very slow updating. The goal is not to like have it be changing during the day and during the night, which you could want to do. I also think that adding a bunch more derivatives, because it's kind of like a slippery slope argument, why don't we just add infinite derivatives and make the protocol more complicated? It's basically, there's some manipulation that can happen when you start to hit the second derivative and third derivative and stuff, and it does add more attack vectors, which to an already very manipulable market.
I guess I'm going to riff on that. I am, in fact, a controls engineer. So the question was actually going to be about introducing a controller and the fact that you're addressing a particular parameter by introducing a controller which has more parameters, which inevitably is the case when you want to create a closed-loop system and regulate a set of properties. But building on the question about the derivative control, I think derivative control in general can be destabilizing. And so in order to actually get a system that is sort of self-calibrating, I'm not sure that the approach is going to work quite as nicely to eliminate the future calibration. If you set that as your primary goal, I think that there are like classes of controller that might be a better suit to that objective. So I guess the real question was going to be, is your primary objective to create something that doesn't need to be calibrated, or is your primary objective to sort of change the stochastic equilibrium of the gas levels to hit a specific target? Because those objectives could actually come into direct tension with each other. And so like even fleshing out the requirements so that you're directly trading off in your controls design, with an emphasis here on, it seems like the good solution for Ethereum would be something that's kind of self-healing, maybe not necessarily as efficient, but if your goal is to avoid needing to calibrate, it's a different class of controller.
Yeah, I think that's great, and I think there's a lot more discussion to do as we continue to scope it out, and I'm not married to the derivative approach. I think if you look at what I showed, it's not just that we're trying to calibrate the derivative, it's actually we're trying to do something which is, we're trying to make this more like a martingale. So I would argue that I'm not just slapping on a derivative, there's a very specific intent behind it, which is that, but I'm really happy to chat more about specifics and would love to chat more, and we're certainly not tied to the exact PID controller implementation or whatever. I think that we would be happy if there's a better idea to do that as well.
Thanks for your time and presentation. I'm an ex-controls engineer, so I love the PID analogy there. But I'm also a finance person, and I want to bring that perspective here. You said earlier in the beginning that some are paying too high fees and others are paying too high in wait time. But that's to assume that fees and wait time are fungible. But to many users, is it not the case that they're actually not fungible, and some people actually would rather pay in wait time? Thank you.
So I have an interesting perspective on this. I actually work at Consensus, which is the parent company of MetaMask, and one interesting thing that we see with users is we give them 3 options, like a fast, a medium, and a slow, and like 95% of users just choose the medium option all the time, which is interesting from my perspective, because it seems like when I write down this model, then I think the users should probably at least be aware of whether they're fast, medium, slow, and even smart contracts, which are huge, oftentimes fill up a whole block and cost $500 or something. You'll see if you go and look at what they clicked based on their gas that they used, it's actually the medium option, which it should be the slow option. So that's an interesting question. I think in this particular context, the priority fee still makes it so that the users who are willing to pay more go first, because it's just a first price versus this posted price system. So in some ways they are fungible. They're not fungible on Solana because they don't have a working fee market, but on Ethereum at least we have a working fee market, even if it is charging users a lot and delaying people.
Great. Thanks, Max. For our final talk of SBC 2024, we have Hao Chung, who's going to be presenting on Rapidash.
Okay, I'm Hao. Thanks for attending the last talk in the conference. So today I'm talking about how to exchange cryptocurrency across different chains, even if some user can collude with the miner. This is And this is a joint work with Lisa, Elaine, and Arvin. So let me introduce the player today. So I'm Hao on the left-hand side is me, and the right-hand side is Elaine. So I have 2 Bitcoins, and Elaine has 30 Ethers. We have agreement that we want to exchange our cryptocurrencies. In this case, what could we do? We can run an atomic swap protocol. So the atomic swap protocol guarantees that either both of us gets the currency we want, or neither of us does, even if one of us is malicious. So for example, to my best interest is I can keep my 2 Bitcoins, but I can get Elaine's 30 Ethers for free, and vice versa. So atomic swaps want to guarantee that even if some players are strategic, we still want to guarantee that, okay, neither both of us get, or either both of us get, or neither of us does. So ideally, we already have the protocol to achieve this. So in the ideal world, all the miners are malicious, all the miners are honest, they will follow the protocol. If you send the transaction to them, as long as the transaction fee is high enough, they will take. However, in the real world, user, for example, me, can collude with the miner, and we can try to take advantage of Elaine. And in the blockchain world, we have smart contracts, and we can use smart contract to split the profit. So it actually makes the situation worse. So here is the question we want to answer today. Can we design an atomic swap protocol that can defend against arbitrary user-miner coalition? So here's the agenda today. First, I will talk about the building block, which we call knowledge coin exchange. I'll explain why the existing solution doesn't work, and I will introduce our solution. And in the second part, I will tell you how do you use knowledge coin exchange to achieve atomic swap. So let's start. In the knowledge coin exchange, here, what we want to exchange is the coins and the secret. So in this case, you can view Elaine as the secret seller and me as the secret buyer, where I want to use, for example, 2 Bitcoins to buy the secret binary string A. So how do we do that? There is actually a very simple solution to this task. So Elaine can just announce the hash. So here, H is the hash. Elaine can just announce the hash of A. And we can deploy a smart contract where I deploy 2 Bitcoins in it. And this smart contract says, anyone, if you can send a pre-image of the hash function to it, such that H of A is the hash value, then that person can get the coins. So in this case, once I deployed these contracts, after that, Elaine's opened the secret. I learned the secret. Elaine gets the coins. Sounds good, right? So in this case, we can view the coin is locked by the hash value. So the secret, you can view it is the key to unlock the coins. But what is this solution looks good, but what's the issue? What's the problem of it? The problem of this solution is, what if Elaine drops out? So sometimes, even the player is honest, you might lose, for example, internet connections, or you might lose your secret key, so that you cannot access to the blockchain. And in this case, me, the secret buyer, my coin is locked there forever. So from the discussion above, we can conclude 2 desired properties we want for the atomic swap. The first one we call it side contract resilient. That is, even if some user collude with the miners, we should not increase our joint utility by deviating from the protocol. And the second one is to protect that if someone drops out, the other honest guy should not be harmed. So in practice, people use HTOC, hash time lock contract, to achieve the knowledge coin exchange. So in this case, I deposit the coins in it, and the coin is locked by the secret A. And additionally, there is a refounding path such that if Elaine doesn't sense the secret within the time T, I can just send a OK message to the contract, and I can get my money back. So this solution actually works really well in the ideal world where the miner just follow the protocol. However, what if I collude with miners? So in this case, the honest Elaine will send the secret A to the contract, but I can ask the miner to just ignore Elaine's transaction. And after time T, I send the OK message to the contract, and I get the money back. And because the honest Elaine already sends the secret A out, so I already learned the secret, but I also get my money back for free. And I want to emphasize that it's really easy for me, the secret buyer, to collude with the miners. Even I don't know who are the winning miner in the next block, because I can just issue the smart contract saying, like, for example, the time T, let's say is 100 blocks. I can say, once you can prove that you are the winning miner, like within the 100 block window, and you don't you don't include any transaction from Elaine, I can split some profit with you. For example, 0.01 Bitcoin to you. And in this case, any rational miner seeing this smart contract will collude with me and try to censor Elaine's transactions. And this echoes the claiming before that because of the existing of the smart contract, it actually makes the coalition forming really easier. And there's actually the really nice work called Match DOC. They suggest you, they ask user to put collateral in the contract. And this selection actually defends against like some specific bribery attack. However, the author also acknowledged that they don't defend against all kinds of bribery attack, and in some cases, users is still incentivized to collude with the miner. So again, the central question today we want to answer is, can we design an atomic swap protocol that defends against arbitrary user-miner coalition? So here is our solution. So we follow the idea of meta HTOC, where we also require the user to deposit some collateral. So in this talk, V is the coins we want to exchange, and C is the collateral. And here we have 4 activation points. And you can see they are P type and C type. So by type, we mean P1 and P2, only one of them can be activated. So for example, if I activate P1, P2 can no longer be activated. However, P1 and C1, they are independent. And the same constraints goes for C1 and C2. So it looks complicated, but no worry. There are actually just 3 cases. So let me go over them one by one. So the first case is the ideal case. If everyone is honest, I'm honest, the secret seller is honest, Meyer is also honest. In this case, Elaine sends the secret A to activate P1. In this case, Elaine gets the payment V immediately, and me, the secret buyer, also get the collateral back immediately. And second, what if the secret seller drops out? What if Elaine doesn't send the secret? In this case, I need to wait for the timeout T1. And here, I need to additionally send another secret B which is sample in advance. And after P2 is activated, I need to wait for T2. And in this case, I will get all my money back. So this, you can view P2 and C1s are the refounding paths. And the third case is we call it burning path. This burning path tries to capture what if some parties is malicious. So this burning path says, if anyone can reveal both secret A and secret B, then this guy will get epsilon. And later on, we'll see epsilon is smaller than V and C, so there are some currency is burned. When I say burned, that means it's totally eliminated from the circulations. And if you're familiar with EIP 1559, the Ethereum's transaction fee mechanism, they also use the feature burning. So the intuition of using C2 is that under what conditions A and B will be simultaneously revealed. So that must be the honest sellers already published A. However, the malicious buyer, I also try to get my money back, even after seeing the secret. So but we require that I have to reveal B to trigger the refounding pass. So in the honest case, A and B should not be revealed at the same time. So in this case, the purpose of C2 is to punish the malicious player. And here the quick acknowledgement is there's also another elegant concurrent work called Helium HTOC, but they actually come up with the really similar idea. But in their work, they focus more on analyzing different kinds of bribery attack of a single HTOC case. And our work focus more on the autonomy swap, as I will cover in the second part of this talk. So two works actually have different focuses. Okay, so in our paper, we show that the protocol we introduced above actually can defend any user-miner coalition. And the key idea is that because we actually burn some of the money, it actually disincentivized 100% user-miner coalition. What does that mean? That means if I'm the user, I post a smart contract, I try to say, oh, if you are rational, please join me. Because of the burning path, there's always some miner will try to defect from the coalition and try to trigger the C2 activation points to get the incentive epsilon. So in this case, any strategic player, for example, I'm the buyer, I'll be afraid that someone will defect the coalition and trigger the bomb. So in this case, I don't want to take the risk. And there is another feature is that to realize the contract above is actually really easy. We have the Bitcoin implementation ensuring that you can only use the really restricted Bitcoin script to realize all the logic. And finally, we called our protocol Rapidash because Rapidash is a Pokemon that can protect the rider and use the fire to attack the enemies. And this is exactly what our protocol does. So we have the burning pass. The purpose of it is to protect the honest user and try to punish the malicious player. Okay, and finally, let me quickly give you examples of the parameters. So these 3 bullets are the constraints of the parameters. Any parameter satisfy these constraints work. And just a quick example, for example, let's say gamma is the fraction of the strategic player miner you collude with. You can just set the collateral as like V over 10, where V is the price. And the time you need to lock is just 4 blocks. Okay, now let me explain how do we use the knowledge coin to achieve a knowledge coin exchange to achieve atomic swap. So let's recall what is atomic swap is we want to exchange different currencies across different chains. So in this case, I hold the Bitcoins and Elaine holds the Ethers. And here is the traditional paradigm to achieve the coin swap by using two instances of knowledge coin exchange. So in this case, Elaine first randomly chooses the secret A. So what exact secret doesn't matter. It's just a uniformly random string. And then Elaine deployed a knowledge coin exchange where the Ether is locked by the secret A. When I say by lock is once you can you compute the hash value of A. Once you can provide A where it matches the hash value, you can get the money. So after that, I also deployed a symmetric contract on Bitcoins where my Bitcoin is also locked by the secret A. And here, Elaine, as the person who chooses the secret, sends A to the contract on Bitcoin. At this moment, Elaine gets the coin, but I also learned the secret, and I use this secret to get the Ether on the other side. So it sounds good. So what if we just deploy like two instances of Rapidash, one on Ethereum, one on Bitcoin? Do we have a dream atomic swap? Unfortunately, not. So if we just deploy like two symmetric Rapidashes on both chains, here is the attack. So both of us just deploy the contract. Here, Elaine doesn't send the secret A to the Bitcoin. Instead, Elaine waits. And because we have the refounding path, right? So after some time out, Elaine can get her money back. But on the other side, Elaine also tells the miner, please delay my transactions. Because if I don't see the secret A, I also want to get my Bitcoin back. But what if my transaction is delayed? And after Elaine gets her money back, Elaine can, at this moment, can send the secret A to the Bitcoin and get my Bitcoin for free. So what is the difference between like two instances and one instance? Why it's fine if there is only one instance, but now we are in trouble if we have two instances on different chains? The key observation here is because at this moment, after Elaine gets her Ether at step 4, the secret has no value. So if you just focus on a knowledge coin exchange, what if I just a simple secret buyer? Actually, at step 6, I learned a secret. I should be happy. If there is only one instance, I learned A at the end. I'm happy. However, in the atomic swap case, in this two instances case, A has no internal value. The secret A is just a lock such that we want to facilitate the coin swap. So as soon as Elaine gets her Ether at step 4, the secret A has no value to me. So that's the issue of coin swap. So one of the most important observations of our work is actually the game theoretic guarantee protocol doesn't compose well. If you just naively combine like two protocols with nice game theoretic guarantees, the resulting protocol doesn't necessarily have the same game theoretic guarantee. So due to the time constraints, let me quickly, let me just give you some intuition that how we tune our protocol so that we can achieve the side-contract resilient atomic swap. So here, our observation is we have to make two knowledge coin instances asymmetric. And here is how we make it. the first change is we have to make it, the Ethereum side have more possibility to invoke the bomb, to invoke the C2 burning path. Because once Elaine tries to get her money back, which is a strategic behavior, she should be punished. However, we also notice that we also need to have a more hash value to protect the coins on the Bitcoin side. And once, there's actually the really intuitive explanation for this is we have two properties for the atomic swap. The first one is side contract resilient. We don't want the malicious party to gain. But on the other side, we also want it to be dropout resilience. That is, if the honest party want to get the money back, the honest party should get. So all the design pattern for this is try to find a good balance such that how easy you can get your money back. If it is really easy to trigger the refunding pass, then maybe, as we have seen, the strategic party may really easy to get the money back and try to attack on the other side. However, if it is really difficult to get your money back, then maybe the other party just drop out for some time window, your money just locked there forever. So we have to tune two instances by adding some, like add one more hash value on the Bitcoin side, or add more conditioning to trigger the bomb to find a good balance between how easy you can get your money back. So in our paper, we have the 4 protocols explaining how you tuned the Rapidash instances on each side to defend against arbitrary user-miner coalition. And second, we also propose another game theoretic guarantee saying like, if the other party has some eternal incentive to attack you, then we guarantee that the honest party should never be harmed. And finally, we have the 4 Bitcoin instantiations and also the Ethereum simulations. And you can find our paper online, and feel free to ask me any question. Thank you.
Other questions? Want to line up at the mic there? Yep, go ahead.
Hi, does this attack hold if you implement atomic swap with adapter signatures? Or any attack that is
atomic swap what?
With adapter signatures?
Adapt version?
Adapter signatures? It's another way to implement atomic swaps.
Sorry, what's your question?
Well, if you don't know the other way, maybe we can talk about it later. But if you implement the atomic swap with an adapter signature,
adaptive signature?
Yeah, if the attack still holds.
You mean if we use the adaptive signature to realize atomic swap, would it be easier?
Yeah, instead of code and hash-based time lock puzzles. Have you thought about it?
Yeah, I don't have a simple answer for that.
Okay.
Max?
So I guess I have one question about how much we expect to burn in like the happy path equilibrium. And I have another question about whether you think this is more about a problem of the fact that the miner has too much control over what gets into the block. And maybe one other direction is just to try and increase the censorship resistance of the chain. And whether you think that would be good for the like cross-chain atomic swapping as well, if both chains are much more censorship resistant.
Yeah, good questions. So how we set epsilon, the amount of burning is, it should not be too large. It at least need to be smaller than V and C. And it also should not be too small, because if you burn anything, then no one wants to trigger C2, then C2 is useless. So actually, the main purpose of epsilon is it has to be set properly to disincentivize 100% of miner user coalition. The intuition is there's always some miner want to defect you and just try to get the epsilon incentive. And in our paper, we have the full calculation. It actually relates to like how much mining power you control. Yeah, this is the first question. And second question is about like the censorship resilience, right? Yeah, this is actually really good questions. So this is true that all this issue comes from the fact that a single miner can unilaterally control what kinds of transactions I can put. If I don't like you, I can just censor your transactions. But for example, like maybe we can use the encrypted mempool, so I don't know which of the transaction comes from whom, for example, like that. Or the inclusion of the transaction is controlled by a committee, not a single person. Then this problem can also be solved. Yeah, that's a really good question.
Hi, very nice talk. I have a question about how, you have a penalty when you receive the secrets of both A and B, but yesterday, like Fan shared work that currently in Ethereum, the builder market is mostly dominated by 3 parties. And I think in this situation, like, it's very possible that, let's say, I'm Hao and I collude with the biggest miner, like Beaver, and I will only send this secret B to this specific builder because I know like maybe over 50% or 60% he will be the actual builder of this block. Then like in this case, no one else will receive the secret B, so they will not be able to, guess this B epsilon things. So like, so in the current situation, if there's centralization in the builder markets or the miner markets, how could this work? That's my main question.
Yeah. I'm not sure whether I understand the question correctly, but I guess the key point here is we have to disincentivize 100% of miner. So that means there's always some miner doesn't want to join my coalition. So in this case, for example, you send secret B to maybe the biggest miner, which only maybe controls 60%. That means there are still 40% who is not on my side. So in this case, we have to set the time lock T1 and T2 big enough such that there's, with high probability within this window, at least one honest miner will win the block. And that honest miner will just like either trigger P1, where everyone, which is the honest case, or trigger the C2 bomb. Yeah, so in this case, it's just like, at least there's only one honest miner, not on my side, then with high probability within this window, we are fine.
So I think the main question here is, like, you're assuming that you're publishing basically this collude to every miner, but my question is, like, what if like they go through the private order flow that only send to like one specific miner?
So in this case, other honest miner doesn't see B, is that case? But so in this case, buyer is the malicious one. So the seller, Elaine here, is the honest guy. So Elaine will send A. So the honest miner will just activate P1. And once P1 is activated, then the transaction is basically down.
Thank you.
Yep, no problem.
Thanks so much. All right, I guess this concludes SBC 2024. Do the organizers have anything else to say? Well, great, thanks everyone for coming.